And yesterday I also talk about application in the field of microelectronics, especially about the LEDs and solar cell and photodetector. So these application was very important, and still people are trying to improve the efficiency of each optoelectronic devices. So continuous research is still going on. The major breakthrough was about the LEDs in 2014 when they got the Nobel Prize. We are using the LED because of its high efficiency. We can save the power because it requires less power when we are using the LED light source as compared to traditional light sources. So that's why LED is widely used these days. Then solar cell. Solar cell research is still going on. However, the pace of research is little bit slowed down, and it is focused on the prime material that can be used for solar cell. People are very much interested in the perovskite solar cell because perovskite solar cell so far now has shown promising features that is useful for the solar cell. But still it has some kind of disadvantages, and to overcome these disadvantages, people are trying to find the solution, and hopefully they will come up with some ideas. And one day, now we are using silicon. Silicon can be replaced by certain kind of material that can be used for the solar cell. That material might be perovskite. Then about, we have also seen the photodiode. So diode that can use the light. So this photodiode is light sensitive device. In simple diode, we are not using the light, but here we are using the light. Photolysis, we are not using any catalyst, but we use catalyst, so it becomes photocatalyst. In the same way, here we are using the light. So simple diode is named as photodiode because we are using the light here to enhance the efficiency, or that can use when we put the light on a diode. Lots of research has been done so far to find out the light source or photodetector or photodiode. These days, two-dimensional nanostructures are promising material that can be used for various applications, not only in the field of optoelectronics, but also other application these two-dimensional material have. When we talk about the photo detection, MOS2 is one of the prime candidate. Lots of research has been done in last 9 years on this application, and hopefully people will continue this trend, and we can get certain kind of two-dimensional material. It may be MOS2 or even some cases combination of two-dimensional material, heterojunction material such as MOS2, RGO, they are trying to use to get the better performance of this photodiode and photodetector. They are using various combination, two-dimensional oxide material, gold plated. So there are several research is going on. Now coming to the today's talk. So today's talk is about healthcare, application in healthcare. Healthcare means in the field of medicine or biomedical. The concept of this application, like we can use a small particle for medical purposes, healthcare purposes, was first, you can say, designed or think by the physicist named as Richard Feynman. In 1959, almost 66 years ago, he was giving a talk in American Physical Society meeting. During his talk, he used the word, "There is plenty of room at the bottom." Those who are physicists, they know this sentence, or even chemists, they also know this sentence. What does it mean? There is a plenty of room at the bottom. So, at the bottom means he is talking about the material. And as you go on the lower scale, deeper scale, as the bigger particle becomes smaller and smaller, then you go the bottom of the material. So scale down the material, understand the material. Earlier I told you, do not synthesize the material, you understand the material. So we need to understand what is at the bottom. That was his thought in 1959, almost 65 years ago. So he proposed that it is possible to build nanoscale machine. Possible to build nanoscale machine where we can arrange the atom as we wish, as we want. So if we can make a certain nano machine where we can play with the atom as we want, if we succeed, then maybe we can able to make such kind of nanoscale machine. And this nanoscale machine can be prepared by chemical synthesis or mechanical. That was his idea those days. Other process was not used. Only to synthesize any particle, chemical and mechanical methods was available. So whatever methods was available, he feel that those days maybe chemical synthesis you can prepare or mechanical manipulation. When we able to prepare such kind of nanoscale material where we can play with the atom, then nanoscale machine can be possible to make. This lecture, after listening this lecture, most of the people thought about we can go to the deeper of the material. We can understand the material. And that was going deeper, reducing the scale or scale down is nothing but thinking about nanoscale, nanomaterial, nanotechnology. When we think about the nanoscale machine, we are thinking about the nanotechnology. I have already explained what is nanoscience, nanotechnology. When we talk about the device which is made up of nanomaterial, we call nanotechnology. So here, when he is thinking about nanoscale machine, device, that is nanotechnology. So the thought come before 65, 66 years ago, and till reality is little far, but we are approaching towards his thought. So that was the beginning of making nanomachine, thinking about nanomachine. There was another mathematician, Albert Hibbs, who liked self-actuated machine. Now, both Feynman and Hibbs proposed medical application for his theoretical micromachine in 1959. Both of them think whether it is possible to make such kind of nanomachine. He said that means it would be interesting in surgery if we could swallow the surgeon. Now surgeon means doctor who can do the surgery. So he thinks that if we put surgeon in our body and if job is done, we can, take out. So swallow means we put inside our body and do the business, do the job, and then take out. So surgeon means maybe nanomachine, what he was thinking. In this way, if you put the mechanical surgery inside the blood vessel and it goes into the heart and look around. So like you explore the area. When you arrive here, first time you don't know where is the department, where is the guest house, where is the... So you explore. Similarly, this nanomachine can explore the various area in the body. So this thought of making nanomachine was proposed in 1959, and after 66 years, 65 years, we are really thinking that this dream will come into the reality, because at this moment we are making the nanomaterial. When we will able to control the synthesis of nanomaterial on Armstrong level, then such kind of machine will be definitely possible to make. As you know, nanoparticle, nanomaterial means which has a size up to 1 to 100 nanometer. And the classical example of understanding the size of nanomaterial is human hair. Many people has human hair, but their diameter is different. Somebody might have 60 micrometers, somebody has 80, somebody has 150, somebody might have 200 micrometer. So on an average, it is around 100 to 150 micrometer. So when you compare this thickness, okay, this thickness, how many nanoparticle will put on this edge? It is about 100,000 nanoparticle you can put on human hair. So when you are thinking about nanomachine, so you can imagine how small these nanomachine will be. So this edge where you can put 100,000 nanoparticle, and such kind of area is available where we can make small devices which are called as nanoscale machine. So nanotechnology involve individual atom and molecule. I told you that when we say nanomaterial, it is 10 to the power minus 9. And that 10 to the power minus 9 is the size of nanoparticle. Each nanoparticle made up of, consists of, proposed of atom and molecule. They have certain atom and molecule, and their arrangement is regular arrangement where individual atoms are holding each other by certain bonds. So they involve atom and molecule. Anything around us, whatever it may be. Whatever it may be means everything around us is made up of atom. Whether you are eating any food, it is made up of atom. You eat anything, it has certain composition. It is made up of something. So we say fiber, cellulose. Whenever you are eating rice or something, they have certain kind of composition. And that composition made up of atom. Not only the food, but in our body also, whatever we have, that is made up of atom also. All these things which we find around us is made up of atom. Shirts and clothes. So if you remember the lecture number 1, where I was talking about the application of nanotechnology for military purposes or waterproofing clothes, we can use certain nano coating that can protect us from the rain or maybe protect us from the bullet. So those kind of, either we can make the cloth made up of nanomaterial or we can coat the cloth to protect from the water. So there are different ways we can use nanomaterial. So this cloth is also made up of atom. Whether it is food, body, cloth, or even air is also a kind of gas molecule. So everywhere we have atom. And when you say everywhere we have atom, so atom is in Armstrong scale. And we are talking about nanomaterial. So nanomaterial is everywhere. The simple thing is we cannot see, but it is everywhere. Nanomaterial is everywhere, within your body also. As I told you that nail, hair, these are the example. And inside our body also, nanomaterial, nanotechnology you can find. So in our day-to-day life, we can have nanomaterial or nanotechnology. In the real world, there are some practical examples. So practical example, UV film on glasses. So you might see the glasses to block the UV rays. This is the commercial application you can see in the real world. Application is already exist, or sun screen to protect our body from burning due to the UV rays. So this protect our eyes, this protect our skin, and TiO2 or zinc oxide material is used in this sunscreen. So this application is available in day-to-day life. The various application in the healthcare area is found or is proposed. For example, for drug delivery or cancer treatment, nanosensor or nanorobots. So these are the possible application from our day-to-day life to medical therapy. It is proposed that we can use some of the application is exist, and some of the application is still going on. So I will explain those applications later on. Nanomedicine means what? Healthcare application means it is biomedical, medical application. So what is nanomedicine? Since we are thinking to use the nanoparticle for medical purposes, so what is nanomedicine? Nanomedicine means it is the nano device using the nanomaterial. So that will be the nanomedicine, which involve nanomaterial, and device is also on the nanoscale. So it can be used for diagnosis or treatment, both way. So diagnosis to detect, treatment means to cure the patient. So both way we can use this nanomedicine. So science and technology of diagnosing and preventing the disease, traumatic injury or relieving the pain, improving human health using molecular tool and molecular knowledge of human body. So detection and treatment. Both way we can use these nanomaterial with the help of nano devices to diagnose the disease, and then what kind of treatment patient will need, we have to think about. Various application in the field of healthcare is possible, like drug, medicine, or detection of disease, or surgery and medical robots. These are the application, major application in the field of healthcare. Application in drug and medicine. So nanotechnology may provide medicine or drug, a certain kind of medicine. It may be capsule, tablet, or powder form. That medicine will be made with the help of nanomaterial or nanotechnology, targeted to the human body, enhancing the effectiveness and minimizing the side effect of other part of body. When we make any kind of medicine, each medicine sometimes has side effect. So when we consume the medicine, we have to think about the side effect. So nano material, since it is in nano size, it will minimize, okay? It is not saying in 100% remove, minimize, because size is small. So chances of side effect will be low because size of nanoparticle is small. Anti-cancer gold nanoparticle are proven to be very effective. For cancer treatment, gold nanoparticle can be used to treat the cancer. Or gold nanoshell absorb particular wavelength of radiation, helping to prevent the cancer. It is a metal, so that it can absorb the certain kind of radiation. And this nanoshell can penetrate the tumor cell. Tumor cell, where cancer is detected, you will find this tumor. And then absorb the radiation to heat and destroy this cancer cell. So tumor means it is made up of cancer cell. This particle, small particle, is used so that they can absorb this radiation and they can destroy the tumor cell. So various elements may be used in addition to gold. Not only gold, we can think about other material that can absorb the certain radiation. So we can use gold or different kind of metal. Those have ability to absorb the radiation. present methods for cancer detection can identify the disease, because when we go to the doctor, sometimes we detect the cancer. But cancer might start few years ago. Somebody has stage 2, stage 3, stage 4. So there is method that is present now. We can detect or identify the disease, that how much the patient has tumor size, which stage he is now. Detection is possible if we visit the hospital. By the time of detection, there are already thousands of cells is already exist in the human body once the cancer is detected. And if there are thousands of cells, it can multiply easily because the multiplication goes rapidly. That's why once it is detected, the number of cell, the cancer cell, started to grow fast and it multiply. It's like 1 to 1. It's 1 to 1, then 2 to 4, like that. It multiplied. So growth is very fast. Detection is available. But how to treat this cancer after detection? So current methods that can use to detect the cancer can provide the information of presence of a cancer. It is only giving the sign that patient has a cancer cell. Then once it shows that patient has a cancer cell, what we need to do? We come to know that we identify the certain characteristics of this disease and nature of tumor. Means what type of cancer he has, that can be decided. But to give the treatment, need biospecies. So biospecies means it involves removal of cancer cell. That is the treatment. After identifying the cancer cell, next is to remove it. That is give the treatment. So can nanotechnology do this job? It is possible that nanotechnology will able to address two possible issues. The first one is detect the change after it occurs. Once the cancer is identified, even after identification, what kind of changes is going on, that information should be collected by this nanotechnology. At this moment, even you go to the hospital, we can identify and get the information that he has certain kind of cancer cell. But by that time, it multiplied. The changes is continuously occur in the body. So can we use nanotechnology to get more information? And then this detection, after the detection, we want more information. But only detection cannot cure the disease. So to cure the disease, we need some kind of treatment. Of course, there are treatments available to address the cancer. But those treatments have certain disadvantages. Like when antibodies in our body that bind receptors commonly found on the cancer cell can be coated with nanoparticle which can be detected using MRI and CT scan. So antibodies can be used which was coated by the nanoparticle, and then it can identify through the MRI and CT scan. So this nanotechnology can be used to detect various kind of molecular marker at specific stages and type of cancer. So it is possible what type of cancer the patient has can be detected by using this technology, nanotechnology. For that, we need to coat the cell with the nanoparticle. Then we can get the information using MRI and CT scan. Now, when we have cancer cell in our body, if we have one cancer cell, it may be exit at any time. But one cancer cell increase to 2, then increase to 3, then 4, and so many cells can be grown. So this number of cells, initially it begin with one cell and it multiplied. So this cell started to have multiplication, and this number of cells when occur within our body, what happened? We have tumor. Collection of this cancer cell convert into the tumor. Now, when we have tumor, and if we go to the hospital, the cancer is detected. After that, there are 2 types of therapy available today. The first therapy is chemotherapy, and second is radiation therapy. Now, these 2 treatments are available. However, these 2 treatments has some disadvantages, and you might seen some people who already gone through such treatment. The one of the side effect is it can attack, it can kill the normal cell. When we have cancer cell in our body, we have good cell, healthy cells. Those healthy cells is also destroyed, killed by this chemotherapy and radiation therapy. So this is the side effect. Of course, this chemotherapy, radiation therapy kill the cancer cell. Simultaneously, it can also kill the normal cell, healthy cell. So that is one of the biggest disadvantages. If you see some patients who has a cancer, you can see the weight loss in his body. So that comes because this normal cell is also destroyed. Radiation is very high. Not only the normal cell, but it can also have hair loss. So hair loss is come because of this chemotherapy or radiation therapy. So loss of hair and attack on healthy cells, these are the disadvantages. So conventional treatment that we are using to deal with the cancer, that can kill the cancer cell as well as the normal healthy cell. So these 2 disadvantages of killing the healthy cells and hair loss need to be addressed, because these are the side effects. So when we look for the better treatment, we always look what kind of disadvantages we have in the present system or treatment. And then we try to work on it. So we want to reduce this killing of healthy cells and hair loss. So is there any other possibility that we can reduce this side effect? So one thought that I already explained, we can use the nanoparticle. We have drug for cancer. So if we use the nanoparticle, cancer drug with a nanoparticle, so that cancer drug with a nanoparticle can be attached to the target, the ligand on the surface. Now, after attaching this nanoparticle to the cancer drug, how we can deal or what we can do? Once we put the nanoparticle with the cancer drug, it can eject to the bloodstream. So when we eject to the bloodstream, how the cancer treatment will be done? Now this is the nanoparticle with cancer drug. And in our body, we have initially, when we don't have cancer, we have healthy cells. So these are healthy cells in our body. So these healthy cells are not cancer cells, these are good cells. And along with this healthy cell, there is a tumor, and tumor consists of cancer cell. So look at the healthy cell and cancer cell. When healthy cells are in the body, they have certain kind of tight junction blood vessel. Okay, they are attached to each other with this tight junction blood vessel. Healthy cell. Both, okay? But this cancer cell is not have that kind of barrier or tight junction blood vessel. Here you can see the break, okay? These are break because it is increasing and making the tumor. But healthy cells having the tight junction blood vessel. Now when we put the nanomedicine into the bloodstream, it will flow into the bloodstream. This is tightly packed, but these are the leak blood vessel, okay? This one, this area or these are the leak. This nanomedicine will goes toward the cancer cell, which has these holes or leak blood vessel, and attack cancer cell. So leaky blood vessel allow nanoparticle to kill the cancer cell. We will put several nanoparticle into the bloodstream, and they will start it to find out the leaky blood vessel, and they will attack this cancer cell. Now what will happen? It will minimize. Of course they will come here also, but it is tightly packed or tight junction blood vessel. So for them it may be difficult to go inside, but it will be easy to attack cancer cell since the blood vessel has certain leaks. So it will minimize the attack of cancer, healthy cell. Remember, it is minimize. It is not saying reducing, okay? It is saying minimizing. So we cannot, each technique has some kind of disadvantages. So it will minimize the effect, side effect of killing the healthy cells as compared to chemotherapy as well as radiation therapy. So this way we can deal with the treatment. At this moment, the traditional methods of dealing with the cancer is chemotherapy and radiation. So in future, such kind of treatment may be possible and we can destroy the cancer cell. So nanoparticles have the potential to be more effectively target the cancer cell and minimize the harm to the healthy cell. Furthermore, the specific size of nanoparticle can allow them to be large enough to prevent the vascular leakage while small enough to avoid the immune detection. So size is very small. It can prevent the vascular leakage. Drug which we will coat with the nanoparticle are delivering more likely to reach their target cell. Target cell means cancer cell. And they can spare the healthy cell in the body. So they will not attack the healthy cell easily, as you can see in radiotherapy and chemotherapy. So this was one of the application. So beside this application of diagnosing or detecting the cancer or dealing the nanotechnology for the cancer treatment, one of the other application in the field of healthcare is drug delivery system. So drug delivery system, we all have experienced corona during last 5 years. So while dealing with corona, you can say nanotechnology was used to make the vaccine. These vaccines were made by Pfizer and Moderna. Nanoparticle, that is lipid nanoparticle. In the specific, they are used for both to counterattack the corona cell using nanoparticle. These vaccines were made. How these vaccines were made to kill the corona? We have enzyme in our body. There are many RNA degrading enzyme in our body that could destroy mRNA. So we have various kind of RNA. When we talk about our internal structure of body, we have RNA. So this many RNA is degrading enzyme in the body that can destroy mRNA. So to deal with this problem, both companies, Pfizer and Moderna vaccine, encapsulate, means to cover the mRNA with lipid nanoparticle as a barrier to protect. Because if we don't cover mRNA, then that mRNA will degrade some enzyme in our body. To protect this, they use nanoparticle. And that nanoparticle act as a barrier. So lipid nanoparticle is act as a barrier. In addition to this, because of our cell are surrounded by membrane that are negatively charged. And it is difficult for negatively charged mRNA to cross the barrier. Because you already coated with the lipid nanoparticle. So now, since you make the barrier, it is difficult. Like earlier example, when you have tied blood vessel, the nanoparticle or the kind of cancer drug cannot attack human good cell, healthy cell. Similarly, this barrier, which is made up of nanomaterial, cannot break down easily. So this is the place where nanoparticle facilitate the transport of mRNA into a target cell. So when we are looking for the target cell, that was corona, this mRNA should go toward the target cell. While going toward the target cell, they should not harm to other component of our body, that is enzyme. So to protect this harmful effect, lipid nanoparticle was used, and so that this mRNA can goes toward the target cell. And this way we can able to give the treatment. These are the two companies who has make mRNA vaccine. These are biological term. If your major is not biology, maybe it may be difficult, but you can just understand these are the two companies, Pfizer and another is Moderna, where you use mRNA vaccine. That's why they were different than the other vaccine prepared by different companies. So this way we can use the nanotechnology for the drug delivery system. So here, as you have seen in the cancer cell treatment, similarly we can reduce the effect, side effect, and this side effect is achieved because of the protection of nanoparticle that make a kind of barrier. So in drug delivery system, we can also use similar concept that was used in the treating with the COVID. So drug delivery and cancer treatment, these are two possible applications. There are several other applications is also possible, such as nanotechnology will allow tiny surgical tool. Tiny surgical tool will be also possible to use when we are dealing with very small area. Now, if we want to deal with small area, sometimes we cut the area, sometimes we put something inside. Depending on what area operation has to be done, only that area will be affected. So if we make some kind of tiny surgical tool, then that tool will be able to operate on our body. So it will again minimize the effect of, we cut our skin or something. And accurate devices would target just the operation area, avoiding widespread damage. So if we able to make such kind of nano tool, we will only concentrate on small areas. Okay? It may be sometime blood vessel is damaged, or we want to destroy some kind of cell, a particular cell that was clotted or something happened. Then there we will deal with that area only. So nano cameras will also give us certain information. Now we have to use MRI scan and other thing, whole body, whole part has to be scanned. But if in future we make certain kind of nano cameras, then we can get or we can detect the certain disease quickly. And it can also reduce the chance that occurs during the big operation. So mistakes can be reduced. Application in surgery, like making surgical instrument that involve nanotechnology. It may possible that we can use coating, we can use very small tool that is made up of nanomaterial, or it has nano size. There are various ways we can make this surgical instrument. Like you have seen the application that glass, sunglass is coated by some kind of nanoparticle. So similarly, either you can coat, either you can make the nano surgical instrument, or you can make some instrument which is in nanoscale. Imagine certain kind of photos of affected area can be possible to take. So nanotechnology has been improved in imaging technology such as micro and nano CT 3D examination. So you can get more detailed information, 3D scan, so where we can detect the affected area which can distinguish the condition between good area and affected area. Tissue engineering, so here when we deal with the skin and something, so each part of our skin has certain tissue, and when we think about the artificial skin, whether we can make the artificial skin similar to our skin, that kind of engineering is tissue engineering. One of the application of nanomaterial, nanotechnology found in tissue engineering, wound healing. So when we cut our skin, the skin automatically heal, joint together. Okay? If you have cut, after certain days, both parts of the skin can join automatically. You don't do anything, you just put the bandage and that skin can join again. That is called as a healing. That is called as a healing. Whether we can make certain kind of nanomaterial, those nanomaterial can act as a healing agent. If that is possible, then this kind of application in medical field will be very useful. Replicas of healing agent, like body has the power, our body has power to heal the skin itself. It creates certain kind of liquid. That liquid make a medium and skin can join. So same kind of property is expected from material, and this material can act with the cell and make a healing process. If we succeed, then that will be again new revolution. Then robotic surgery. At this moment, still we are using the robots in many operations, but robots with the help of nanotechnology, small robot can be used for the operation. Or orthopedic surgery, where we cut something is broken, there we can use for cut or broke means bone. So bone healing can be done. like skin can heal. So bone is cut, so whether it can enhance, it can improve the bone healing process. Can we use nanoparticle there, nanotechnology there? Cardiac surgery, so nanotechnology can be used to design and develop smaller, more effective cardiac instrument. These days, cardiac means disease related to the heart. We are using some kind of tool, but if we make the tool which is at nanoscale, then heart surgery will again be more easy and effective as compared to today's technology. Pathogen detection, so nanotechnology enable the instrument that can detect pathogen that has colonized in surgical areas or locations. So pathogen is another application where nanotechnology can be used. So I was talking about the nanorobots. Nanorobots, at this moment, we don't have nanorobots, but if you remember today's second slide, Higgs and Feynman was predicting that we can send the surgeon in the blood vessel and he can explore the area in our body. So if we able to make such kind of nanorobot in the future, then we can of course use for the treatment and detection of disease. So in future it is expected that such kind of robot can be possibly made to detect and treat some kind of disease. Besides this, nanotechnology can be used, or nanorobot can be used for arteriosclerosis, where the area is affected by the fatty or fat that can reduce the size of blood vessel. Because if the fat is developed, we need to, that fat is called as a plaque. So this is the blue color, is the plaque or fatty area, and this is the blood cell. Originally it has this much diameter, but due to this yellow color, the fatty surface, it is reducing. Now blood is not moving because of this diameter is getting reduced, and one day the pressure will come, the blood will not pass. So to deal with such kind of situation in a certain part of our body, we can use the nano robot to deal with this situation. And in future, lots of applications are proposed with the help of medical robotics. Those applications can be possible to use in biomedical instruments, surgery, pharmaceutical, diabetes monitoring, cancer detection, and targeted drug delivery. Two ways nanotechnology can be used: separately making the drug delivery system or making nanorobots. So both way research is going on in the field of medical. So robots is injectable. Can we put inside the body? Those kind of robots in the future can detect the tumor in the blood vessel and kill. So that time we can do the treatment in situ cancer treatment if we make certain kind of robots. Nanosensor is another application in the field of medical. So we have various sensors in our day-to-day life. But when you go to the maybe hospital, sometimes they put many things on your body. So those are sensors, like they detect pulse, heartbeat. So they are sensor. So sensor is one of the field where nanotechnology can be used. So while making this nanosensor, nanomaterial or nanomaterial which can sense quickly, effectively, can be used so that we can able to make those sensor and get the information, fast information, effective information for monitoring various, areas in our body. So such kind of sensor may be used to monitor our physical conditions, physical parameter within our body, such as temperature or detecting the pulses and so on. So these days there are sensors, but their size is comparatively big. Comparatively big. If we make the small sensor, then their size will reduce. And if we reduce the size, it might get good information. Photodynamic therapy is another example. Photo, light. Dynamic therapy, therapy means treatment. Something that can be done with the help of light. Maybe laser. You already know laser has lots of application in biomedical. So particle is placed within the body and is illuminated with the light from outside. So light is used for the treatment. That is called as photodynamic treatment. So light gets absorbed by the particle if the particle is metal. Same thing I explained you before. Like metal particle can absorb the light and energy from the light will be heat that particle and surrounding tissue. So energy will be provided to that metal particle from outside. From where? It will be provided by the light. So like laser has certain kind of energy. This energy will provided to that particle and that particle will heat up. And once it will heat up, it can target the surrounding tissues. So light may be used to produce high energy oxygen molecule which will chemically react with the and destroy most of the organic molecules that are next to them like tumors. So this metal or nanoparticle which will absorb the light and heat up or generate the heat around that nanoparticle can able to deal with these tumors. This therapy is also appealing for many reasons. Now we want to have the operation we cut. So this phototherapy, we don't have to, make big operation. So in future, maybe nanoparticle can possibly go into the body and outside we will use light. So there are many advantages. Since we are using the light from outside, it will not affect the body as it is affected by the chemotherapy. So photodynamic therapy is a non-invention procedure, means it is not really we have to go into the body. It is non-invention, means it is not touching to your body. So you are putting light from the outside. So that can deal with the disease detection, growth, and tumors. Besides this, various health-related uses of nanotechnology exist to deal with the bacteria, viruses in our body, or genome sequencing is the area where lots of research is going on, tissue engineering, I explained, and nanotechnology can be used to improve the human life as well as animal life. So advantages of nanomaterial nanotechnology are possible to deal with the treatment and for the detection, especially the drug delivery, and it will reduce the side effect and provide high efficiency. Molecular targeting by nanoengineering device. If we make the small device, you can able to deal with the molecules. Detection, diagnosis of disease relatively easy and fast. So sometime present technique, if we want to detect the cancer or something, it needs some time, maybe 1 day, 2 day, or 3 day. You cannot get the result quickly. So that process of detection may possibly reduce. Once we get the more information, we can start the treatment immediately. So if detection is fast, treatment will be given quickly and patient might recover. No surgery is required. In many cases, we will not cut the body. Okay, we might use robot take out, we use light from outside. So in many ways, operation might not be used to treat with many disease. So disease can be easily cured. Now, last slide for today's class is the disadvantages. What are the disadvantages? So far now, you have seen everything good. So we feel that, oh, nanorobot will be, and we can deal with that. But still, it is a little long way. This application might have some kind of disadvantages as well. These days, medical treatment is not so cheap. It is still expensive. And if we use certain kind of nanotechnology in it, treatment might be expensive because what kind of material we are using, what kind of nano device we are using, depend on that, the cost might be high. Patient destruct. So it might possible that some of the treatment will not be possibly used for certain patients because of his own conditions. Ethical issue. Now, ethical issue means whether we can inject something in our body. I told you nanorobots, but at this moment, it is not allowed. That will be the ethical issue. Implementation difficulty. Sometimes, even though the device will be very small, but how to inject, that implication difficulty is still exist. And environmental pollution, what kind of material we are using, and after maybe surgery we are throwing. So this is the last slide for today's talk or today's lecture. I have explained you that nanomaterial or nanotechnology can be used for various applications in the field of healthcare in near future. Now, the research is underway, and in future, we might see some of the application will come into the reality. Only the application which has direct injection in our body may be questionable, but there might be some solution find, and that treatment will also able to use. So with this, I will stop here. If you have any question, please ask question. Thank you very much. Any question? At this moment, nanorobots for injecting in the body is not made, but it is proposed. The research is going on. And, after making nanorobots, they have to test and then approve. As far as I know, maybe, when we put something in our body, it is a little harmful sometimes. What kind of material it is made up of. So, nanorobot is not made. We have cameras, then in the stomach that can goes, but this robot which we are talking about, we will put inside the body and operate from the outside. Okay, it may be battery based and we will operate it from outside. Now we are putting the camera, okay, so that still has no connection and then we can take out. Okay. So such kind of, because if robots want to move freely within the body, so that's why they called as nanorobots. So it's kind of, risk. Okay, so I will stop here. We still have 15 more minutes. Thank you very much. Let's have a break for tea then. Thank you.
So it is a privilege to introduce my supervisor, Professor Dr. Venkatesh sir, for this session. So Professor Gudipadu Venkatesh is an assistant professor in the Department of Mechanical Engineering at the National Institute of Technology, so NIT Warangal, India. He holds a Master Technology, MTech and a PhD in Mechanical and Industrial Engineering from the Indian Institute of Technology, IIT Roorkee. With over 10 years of experience in teaching and research, Professor Venkatesh's primary research interests include the application of microwaves in manufacturing processes, nano finishing of advanced materials using hybrid abrasive flow machining, HAFM, and surface engineering. He has successfully supervised 2 PhD students with 4 others currently pursuing their doctoral research under his guidance. Professor Venkatesh sir has completed 1 funded research project and is currently working on another. He has authored more than 45 research papers in reputed journals and conferences and holds a patent for his work. In addition, he serves on the editorial boards of 5 academic journals and has delivered around 30 guest lectures on various topics related to his field of expertise. Through his teaching and research contributions, Professor Venkatesh continues to make a valuable impact in the field of mechanical engineering. So now I am introducing Sir Venkatesh sir for this session. Please welcome sir for this session. Please begin first.
Good morning. So let us welcome to So I guess my voice is clear. So now we are in the 4th day of the course. So I hope everyone enjoying the sessions with some laboratory arrangements, live demonstrations, etc. So coming to today's session, so our course is majorly on nanomaterials. So we have learned several basic things about nanomaterials, etc. Now we will see some applications. So where do we use finishing? So nano level finishing in healthcare applications, finishing of implants, etc. So the major outlines of the presentation will be discussing on conventional finishing processes and limitations and advantages of conventional finishing, introduction to abrasive flow finishing process, and several things about surface finishing challenges of AM components and future directions, some case studies, etc. So we all know what are finishing processes, right? So we have conventional finishing and non-conventional finishing processes, etc. So in conventional finishing processes such as grinding, honing and lapping process, so whenever you finish the materials, so there are some constraints with respect to the geometry of the material. Like you can finish only a flat workpiece or a cylindrical internal surface and the external cylinders using cylindrical grinder, and sometimes some concave surfaces using some processes like grinding, lapping, honing, etc. So in these processes we use fine abrasive particles which acts as a tool material. So these fine abrasive particles will remove the workpiece material in a form of a chips. So these chips are in microns and nano level. So the material is removed in micro level and nano level. So these processes are not a complete machining processes. These are finishing processes. Means the material removal will be very low. Okay? Material removal will be very low in milligrams. So there are certain processes where we get cross-hatch pattern. So when we have a rotary and as well as translatory motion, so then there is a chance of getting some cross-hatch pattern, and we have some applications for getting the cross-hatch pattern, etc. in the finishing. And there are some difficult to finish materials, mainly non-metals. So non-metals such as some, let us say some ceramics which are brittle in nature. So it is difficult to machine using a conventional processes because the tool is directly in touch, directly in contact with the workpiece. So whenever the tool is directly in contact with the workpiece, there will be a lot of machining forces generated, okay, frictional forces, and due to that load, there is a chance of breakage in the material and the finishing is difficult. So these are some of the limitations. So one is the geometry. If the geometry is complex, how do we finish it? And the second is, if you want to finish a non-metal, or if you want to finish up to nano level, Armstrong level, then we need some advanced processes. And why high precision is essential in healthcare applications, in implants, etc. Why high precision is important? So precision ensures components meet exact design specifications, enhancing functionality and reliability. So basically, surface quality matters in several aspects, like micro electromechanical systems. Surface functionality and reliability will matter in aerospace components, automotive components, biomedical fields, medical implant industries. So everywhere, like wherever the components are subjected to friction, when you are assembling 2 or 3 components which are subjected to friction, then there is a chance of wear. So our target is to reduce this wear. So we need high-end finishing. We need nano-level finishing in order to achieve that. And there are some aesthetic appearance purpose. So we do required finishing. And coming to challenges, surface finish challenges, the components, the complex components which are manufactured using additive manufacturing. You can see several implants here, several complex implants, orthopedic, dental implants, and several implants are 3D printed, okay, are 3D printed. We will also see the lab today, okay, 3D printing, metal 3D printing lab, and as well as our lab, okay, so abrasive finishing. And we'll also plan a Siemens visit as well, okay, this is not done for your batch, okay, so that also we'll plan. So in order to address these issues, okay, so what is our problem? Our problem is if the components are very complex in nature, so how to finish them and how to deburr them, right, and how to radius them, such a complex geometry, we need certain advanced process, not like grinding and honing lapping, okay. Grinding, honing, lapping can be possible only for the simple geometry. And when we see the capabilities of several finishing processes, finishing in micro level, nano level, and even in Armstrong level. So there are processes such as grinding, honing, lapping, abrasive flow machining, magnetic abrasive finishing, magnetic float polishing, magnetorheological finishing, and some hybrid processes. So in all these processes, we see what are the capabilities of these processes. You can see the RA value in nanometer. So this is the capability of grinding, this is the capability of honing, and we can observe the capability of abrasive flow machining. Okay. So our target is to reach the nano level finishing of the components, okay, of the complex components. So I am working on one particular method. The name of the method is abrasive flow machining. So this method, this setup will achieve nano level finishing of the complex geometries. So what are the general challenges in the modern metalworking industries? Development in material science. Probably you have seen several cases, several conditions, like how the material science is advancing and how the new alloys and new materials coming in the research field and as well as in the industry. So how to target them and how to make a possible solution for achieving the required specifications. So one solution is abrasive flow machining. So abrasive flow machining is a process developed during 1960s. So it's not a new. It is developed in 1960 by Extrude Horn Corporation in USA, and it got patented by the company, so that particular technique. And this particular technique comes under the advanced machining process and as well as the advanced finishing process, and this is capable to deburr, radius, polish and remove recast layer of the finished component, which are finished to difficult components, and this is used to finish the complex internal passages of the components, etc. So here I would like to show the principle of abrasive flow machining. Okay, so the major principle and material removal rate mechanism. So in this particular process, there are three major components. So one is machine, second is the flexible tool, and the third is the fixture, okay, where we fix the workpiece. So the machine here we are using is two-way acting hydraulic setup. Can you see the image? So we are using a two-way acting vertically mounted hydraulic setup. So using this setup we can control pressure, okay, we can control flow volume, flow rate, right, of the hydraulic pressure, etc. Okay, how do we apply? And we have a semi-solid tool which is flexible in nature, which is a kind of the slime, kids who are playing with the slime, right? So we know how the slime behaves. So this kind of material is mixed with the sharp edge abrasive particles, and that is pumped in between the workpiece. So let us say here we have a workpiece, a cylindrical workpiece, and this semi-solid media is pumped to and fro in between, flowing in between the target surface. So this is our target surface. Okay, when you pump this media under high pressure, okay, which pass on the target surface, then the abrasives present in the media will flow on the work surface, hitting the asperities at certain force which is generated by the extrusion pressure applied. So due to that abrasion will take place. So due to that abrasion will take place, and the abrasive particles present in the media will remove the material in microchips and nanochips. So this process, the initial roughness itself is in microns. Means if you want to finish any component, the initial roughness itself we maintain in microns and we reach to nano level. Okay, it's a sophisticated process. It's not like the rough is converted to smooth. Already the taken workpiece is in smooth. We are going to nano and Armstrong. Okay, for several applications, like for medical applications, aerospace, defense applications, where we require high level finishing, there we use. The workpiece dimensions you are saying. So we need to prepare a fixture based on our dimensions. Okay. So once I'll show the video, you will get some idea. Yeah. So this is a technique I'm talking about. So the yellow color shows the abrasive media, and the blue color shows the workpiece. And we have a, while pumping, these abrasives are with a certain axial force, they are, okay, abrasion is taking place. You can see here, so this is a workpiece, and non-cylindrical hole, internal finishing and as well as external finishing is done with abrasive flow machining. So this is a bit difficult to use a simple process. Okay. So in this video, you can see the semi-solid media. So they are showing the abrasive particles. So we can use silicon carbide abrasives, aluminum carbide, okay, aluminum oxide and boron carbide, etc. can be used. You can see the media how it looks like after mixing with the viscoelastic polymer. Okay, so we use viscoelastic polymer gel for mixing the abrasive media. So this is a flexible tool I am talking about. So this flexible tool is pumped in between the work surface. So where in the video you can see they are using a one-way abrasive flow machining. They are pumping that semi-solid media with a high pressure, and the media is coming out from the workpiece. Say this is the workpiece. These are the manifolds used in our automobiles. So this media is coming out from them. While coming out, actually it is doing that radiusing, it is doing that deburring, it is doing the required correction. So we need to control that. So you can see the complex micro holes are removed, and multiple holes can be removed, and this is a tool. So this is a flexible tool we are talking about. So some automobile components, some complex geometry. Okay. So after finishing, they are removing the media. Okay. So the media property is very important here. I will explain after the video. So like you can see, these kind of components which are casted will have several issues after casting. So we require post-processing of these components. Okay. Because to radius them, to deburr them, to finish as per the requirements. So we do a lot of finishing techniques required. And 3D printed components. So using 3D printing we can print several complex geometries. So using 3D printing, like 3D printed components can be super finished. And aerospace industry, several components can be finished up to nano level using this particular process. Finishing of a cross holes. A straight hole we can use some process, some simple process, but finishing of a cross hole, finishing of a blind hole. So finishing of extrusion dies, which are complex in nature, like you can see the channels. So how do we finish the channels? So aluminum extrusion dies with different shapes. So finishing of non-metals as well. So ceramics finishing and polishing of several opticals, bent pipes, okay, and metallurgical molds which are very hard with complex geometry. So mold polishing, even finishing of screw threads, glass mold polishing. So heat runner inside hot polishing. Yeah. So I think you got some idea about the process we are discussing. So we are using a novel flexible tool for finishing the complex geometries. So this tool, which is flexible in nature, will have a viscoelastic properties. So it will carry viscoelastic properties. So what is this viscoelastic? So there is a lot of study on viscosity and also elasticity behavior of the polymer which we are using in the study. For example, like when you brush your teeth with a toothpaste, so toothpaste viscosity is different and it is having different behavior, like it's kind of a viscoelastic behavior. It's a toothpaste gel. If you add some salt particles in a toothpaste and brush your teeth, okay, you are applying certain pressure and you are brushing your teeth. So the result is your teeth will shine because the paste is carrying the salt particles successfully and you are reaching the target finish. So the finish is our finishing the teeth. So you are reaching and you are applying certain pressure and then brushing. Okay. Similarly, if you add some sand particles or abrasive particles and brush your teeth, what happens? Blood will come out, right? Because of the nature of material you are adding. So if you add abrasives, abrasives are hard in nature and they are having sharp cutting edges, the blood will come. Okay, but however, you are using a media which carries your tool, right? Similarly, like when you add sand in a glass of water, so the sand will settle down. Means you cannot pump water and abrasive here. If you add sand in a oil, then it will not settle down because it depends upon the viscosity. It depends upon the viscosity of the medium you are using. So whatever the media you choose, whatever the gel you choose, it should have certain viscoelastic nature. Okay, some people are using rubber milk, the natural rubber milk getting from the trees. They are taking that rubber milk and then adding abrasive particles in it and allowing it to become viscous, and then they are pumping that for finishing. So there is a lot of study on the type of media used in abrasive flow machining and its properties. So we need to study the thermal stability of the media used and the behavior of the media, and as well as the temperature properties. So when we are pumping the media to and fro, so what is the difference in the temperature, right? Because we are doing abrasion process. So what is the difference in the temperature? And there are studies on PGA analysis, thermogrammetric analysis of the media. So to see if there is any endothermic and exothermic reaction taking place during the process. Okay, so here the principle explains you in abrasive flow machining media quickly abrades the peaks of the rough microsurface at the first, after which the valleys become slightly abraded as the peaks flatten into plots. Eventually a smooth and uniform profile is produced with no trace of the original surface. So this is what happening during the process. So these abrasives hitting the target surface, and then some small microchips are removed from the target surface and the process will continue. The third important component in the process is tooling, as the sir asked, like how the tooling is designed and for different geometry, for different workpieces, how the finishing is possible. So the major role of the tooling is it holds the workpiece and as well as it guides the media so that the media will pass on the target surface. So these two things we need to keep in mind while preparing the tooling or the fixture, right? So when we prepare a fixture, we need to keep in mind two things. One is a proper seat for your workpiece. You can see here, this workpiece is different and this workpiece is different, this workpiece is different, and there is some complex fixture here. So for your designed workpiece, for your desired geometry, you need to first prepare a fixture. That fixture will allows the workpiece to sit and as well as to guide the media so that the media will pass on the target surface. So these two things. So you can see the applications in turbine engine parts before and after, in the medical implants, finishing, and whatever the video we have seen. So we have seen all these kind of applications. And to have some clarity on the finishing of bent pipes and the complex geometries and the flexibility of the media. So this is a mixture of some mixing oil, and in the laboratory you will see the media preparation and as well as the fixture preparation, how the fixture is prepared, and then how the finishing will take place using this flexible media. So you can see here, this is the workpiece, so how the media is pumped to and fro, and then how the finishing is taking place. Yeah. So whatever the setup we developed based on our project, okay, based on our requirements in the lab. So this is the design model So initially we thought of designing the abrasive flow machining or vertically acting abrasive flow machining. So this is the design model and this is the fabricated model, and you can see the fixture. So this is the fixture. So if you disassemble the fixture, you will see the seat for the workpiece and as well as the guidance of the media, so that the media is flowing to and fro on the target surface. Okay, so we are targeting to finish the internal geometry of this workpiece. Okay, we are targeting to finish the internal geometry of the workpiece and how it can be done and what are the parameters that are playing a role and how the finishing takes place, etc. So this video will shows you the to and fro action, what we expected. So these are the medium cylinders, these blue colored medium cylinders, and 2 acting hydraulic cylinders are there. So we fill the flexible media inside one cylinder and we'll pump the flexible media to and fro, passing through the target surface, so in between the fixture. So this is a simple AFM. We'll see some advancements, how people worked on different aspects, etc. So this is a to and fro action. Yeah. Now we understand the principle, right? So what is the principle and what are the major components? As I said, 3 major components. One is the setup, second is the flexible media, and the third is fixture. So we have designed, the literature says the influencing parameters of these 3 major components. So when we take the machine settings, the major machine, extrusion pressure will play an important role. So what is the pressure you are applying on your abrasive media? And based on that pressure, your axial force will vary. So the abrasive particle which is carrying, the media is carrying an abrasive particle, will have certain axial force with respect to the applied extrusion pressure. So that by varying the pressure, actually we have influence on the result. Second is the number of cycles and how many cycles. Like when we pump the media from one cylinder to another cylinder, we calculate it as 1 cycle. Okay, so when the media is pumped from bottom cylinder to down cylinder and then from down to bottom again, so we calculate it as 1 cycle. If you increase the number of cycles, the surface finish rate will vary. Okay, if you increase the number of cycles, the surface finish will increase, and also the material removal also will increase. So this is also one of the important parameters. Flow volume and its speed. So this also can be controlled by using the machine. So if you know the cylinder diameter, etc., and the volume, etc., we can be calculated and we can have the control on the speed as well. Coming to abrasive media. So abrasive media viscosity plays an important role. So what is the viscosity? Whether it is a low viscosity media or high viscosity media, and how to measure the viscosity of the media, and media rheology. So to know more detail on the viscosity, like shear rate, instantaneous viscosity while pumping the media. So what is the viscosity of the media after finishing, before finishing, and instantaneous viscosity of the media when you are pumping, when it is flowing through the surface. So what is the viscosity, etc. In detail can be studied about the media rheology. Next, abrasive type, size and concentration. This is the type of the particle you are choosing and the size of the particle and the concentration. So you can choose either abrasive as a silicon carbide or any other abrasive particle, and size and concentration also matters. So if the abrasive size increases, then your material removal increases, whereas your surface finish deteriorates. Okay, if you use coarse grains. If you use fine grains, the surface finish will improve better, whereas MRR will be low. So there is an impact on abrasive size and concentration. Concentration means, so the percentage of abrasives you are mixing with the media, that polymer gel. Say if you are mixing 50% of polymer gel with 50% of abrasives. So what is the impact? If 40% of abrasives mixed with 60% of polymer gel, so what is the impact? So like that, there are studies to know the impact of abrasive concentration. Coming to tooling and as well as the workpiece, restricting passage length and area. So while designing a fixture, how you are restricting your passage to have a better control on the velocity and the pressure of the media flowing towards the target surface, and the type of workpiece you are choosing. So what is the hardness of the workpiece? So depending upon the type of the workpiece, you need to choose the abrasive type. Okay, you need to choose the abrasive type, size and concentration also. Right? If you are using very hard material like cast alloy and nickel based alloy, etc., then accordingly you need to choose the abrasive type. So this is the media preparation. So we will show a small demonstration also in the evening. So the abrasive particles mixed with the mixing oil, we use naphthenic based oil here, and the polymer gel, and how it becomes a flexible media, a semi-solid media, and how it can be tested, okay, and how it can be used for functioning, okay, for processing, for finishing, etc. And we use different grades of silicon carbide particles like 120 size, 80, 60, even 180 size, etc. So under scanning electron microscope, so we have identified the size of the particle, right? Size of the particle we are choosing, and also the shape of the particle we can identify. So while pumping the media, so we observed before and after finishing of the sample under the defined pressure, and we also working on a 3D printed components which are having applications in medical, okay, mainly fracture plates used in fixing the ankles. So these fracture plates are planned to finish using abrasive flow machining. So we are studying before finishing and after finishing of the fracture plates. So these are the 3D printed components. So as a part of lab, we will also show the 3D printed lab, 3D printing lab, and as well as our finishing lab. So you will get some idea like what we are working on. So some basic study we have done on a design fracture plate. So you can see here, so this is a design fracture plate and this is a original fracture plate, and we have not used our machine here because our machine was under fabrication during the study. So we used a machine which is available in CMTI Bangalore, so abrasive flow machining. So they pumped the media to and fro on a sample, and these are the parameters we used in the study, like the abrasive grid size used and the viscosity, and you can see the density, abrasive percentage, pressure, etc. varied. And we observed the finishing of the samples by varying the number of cycles and as well as by varying the extrusion pressure, and we could achieve some kind of a mirror finish before and after abrasive flow machining. And also you can see, so these are the conventional machining marks. You can see the deep tool marks which are found by a conventional machining, and the deep feed marks or the deep tool marks are removed by abrasive flow machining, right? So this is not a final achievement, okay? We need to work on improving better. We need a mirror finish, mirror reflection, and also we need to take more complex geometries for finishing. Yeah. So these are some of the results. These are some of the results at different cycles, 50 cycles, 150 cycles, and 350 cycles, 450 cycles. So as I said, one cycle equal to like when we pump from to and fro action, right? So here we observe that 450 cycles we are getting certain finish. Okay, so let us say RA value from 1 micron to say some, as per the scale here, So the finishing is, RA value is not exactly, yeah, you can see here. So the maximum peak here is say some 10 micron, and here you can see some 0.1 etc. right, 0.1, 0.2. But this is not sufficient, and also we observe that it is taking more time. Okay, 450 cycles is huge, so we need to spend a lot of time for finishing. So these are some of the observations on the fracture plate, and some applications of this particular process, especially finishing the recast layer which are formed by EDM process, and finishing the 3D implants, 3D printing implants, 3D printing components. Nowadays is a very important application. So in aerospace industries also, people are looking for a novel process for finishing the 3D implants. In the recent ISRO projects brochure has released, I think some might have seen. So there also there is one of the project requirement where they are looking for a process which can finish aerospace components which are printed by using 3D printing. Okay. In that applications we can see how the abrasive flow machining and other processes can be utilized. Yeah. So the literature says that 80% of the cost of the final finishing component comparatively manual. So 80% of the cost will be saved. Like if you use a mechanical process comparatively manual. So the process is easy to operate, and it is used to reach the high tolerance. It can be used for high-end finishing, and it can finish inaccessible areas. So there are several advantages, and the major disadvantage is the process is low, means slow. So it suffers with low finishing rate, and a lot of processing time is increased, which will implies the increase in the manufacturing cost of the overall component. Okay? Since the process is slow, and also the material remold rate is very low. It is in milligrams, so the material remold rate is very low. So in order to address these limitations, there is a lot of research started, okay, to hybridize the process. So we will discuss few. So to hybridize the process, many people have tried different techniques, different approaches to hybridize the process. So what is hybridization? So combining two or more techniques in order to achieve the efficiency of to improve the efficiency of the process. So how the abrasive flow machining is hybridized, and what are the results, and what are the what are the major achievements of this hybrid AFM, etc. So we will be discussing. So there are some magnetic field based abrasive finishing, and there are ultrasonic assisted abrasive finishing. There are some rotary based abrasive finishing, and drill bit guided, centrifugal guided, and electrochemical abrasive finishing, etc. Right? So the people who are in mechanical background, I have seen some 2 to 3 or 4 participants specifically from the mechanical, and of course it's a combo of different people. So we understand how this hybridization help, and what kind of hybridization they are doing, and how they are addressing those limitations. So hybrid AFM types I would like to show again. So magnetic based abrasive finishing. So it's again further divided into 2 types: magnetic assisted abrasive flow, magneto-rheological abrasive flow, and people tried chemical based abrasive finishing. So electrochemical abrasive flow finishing, centrifugal based abrasive flow finishing. So here centrifugal assisted abrasive finishing and spiral assisted abrasive finishing, rotary based, ultrasonic based, etc. Yeah. So there are several types, and every hybrid variant is one PhD work. Okay. I worked in this particular area where I used ultrasonic based, right? So using ultrasonic vibrations, how the finishing is improved further, and how I address the limitations of conventional abrasive flow machine. Let us see one of the hybrid variant. So magnetic assisted abrasive flow machine. So here also the principle is same. So here you can see the abrasive media and the two-way acting hydraulic setup and the workpiece tooling, and they are using a cylindrical bush as the workpiece. And when we pump the media to and fro, okay, when you are pumping the media to and fro, so the media will flow on the target surface at certain extrusion pressure. And we are looking into the media viscosity, media flow volume, media flow rate, and we are looking into the constraint created. Everything is taken care. So apart from that, so there is a modification in the setup if you observe. There is a modification in the setup if you observe. So the modification is, so electromagnets are arranged, okay, magnetic field is arranged around the tooling. Okay, when you vary the magnetic field density, okay, when you vary the current, so how the media is reacting under that magnetic field. So they tried using magnetic workpieces, magnetic materials, and also non-magnetic materials as the workpieces. And they added some iron particles, small iron carbon particles in the media, and they prepared a different media and they pumped. So when the magnetic field is on, they observed that these iron particles mixed with silicon carbide are having more impact in the tooling zone, because the tooling zone is under the control of magnetic field. So the result is there is more active abrasive grain density. Means the abrasives are participating more when the magnetic field is applied than without magnetic field application. So they studied how the finishing rate improved and how the material removal improved, so when the magnetic field is on. They also studied by varying the current, by varying the other parameters related to magnetic field, how the impact on finishing, etc. So they studied. But they did not study more on the magnetic viscosity of the media and what is happening inside to the rheology of the media. So they studied mechanically like how the finishing and how the material removal takes place when you are pumping the media to and fro. So these are some of the same images like before finishing and after finishing. So how the surface has been finished. So this image is taken from the paper. So like you cannot see the smooth finish. Yeah. As I said, they did not study more on the rheology of the abrasive media, like finding out the magnetic viscosity of the media. In the next year, in the 2004, another researcher has developed the same kind of setup, but he concentrated more on magnetorheological properties of the media. In the previous case, in the year 2002, they have conducted that particular study and they got PhD. Okay, and this 2004, so all these are done in IITs only mostly. So they work more on magnetorheological abrasive flow machine. So what is the difference? So they studied more on the rheology of the media. I will show you that. So when you are pumping the media to and fro, as I said, they added iron carbon particles inside the media, and we also have the silicon carbide particles in the media. When the magnetic field is applied, then these carbon iron particles are forming like a chain. This chain formation is possible when you apply magnetic field around the tooling. And what is the purpose of this chain formation? They explain in a schematic. So when the silicon carbide particle is surrounded with a carbon iron particle chain, when the magnetic field is applied, then not only the abrasive particle will have more interaction to the asperity, but also the abrasive particle will have more axial force because of the surrounded iron carbon particle. So the hitting of the abrasive tendency has been increased. Okay, so these are the asperities. The abrasive hitting tendency has been increased. Okay, and also there is more active participation of abrasive particles when the magnetic field is applied. So people are working on synthesis of abrasive particles. Okay, people are working on the type and shape of the particle and the iron carbon particle size, okay, to have a better control on the process. So this process, this magnetorheological finishing process, there is one project, ongoing project, in even ARCI people are working on finishing an optical surface. Okay, so they prepared for a bulletproof opticals. Okay, they want Armstrong level finishing. So for that actually they are developing a magnetorheological finishing process where they mix this media along with the iron carbon particles, and the chemistry is also involved to study the synthesis of the particles, and several aspects they are working. Not only the mechanical abrasion, but also there is more to study about the rheology of the media, so which will have a lot of physics and as well as the chemistry as well, to have a better control on the media while finishing. So their target is to finish their components which they are using for like safety purpose. Okay, like as I said, the opticals, bulletproof opticals which they wear, okay, when they required. So how to finish them? Okay, so another advancement in hybrid AFM is centrifugal force abrasive flow machining. So this author tried to control the process by introducing centrifugal force. So how he achieved? So he took the fixture design as a challenging in this particular process. Okay, so he made a patent also on the fixture. I will show the image of the fixture. Yeah, so this is a simple fixture and some addition in the fixure with a rotating attachment and as well as with the centrifugal rod. So they fixed a centrifugal rod and they created a fixture with a rotary mechanism. So this centrifugal rod is inserted in a cylindrical bush. So you can see here. So this is a centrifugal rod and this is a fixture, and they rotated this centrifugal rod and the centrifugal force is generated. So this centrifugal rod is inserted in a cylindrical bush. So our target is to finish the cylindrical geometry in this particular process. So how they achieved, you can see here. So they worked on finishing of cylindrical bush, that particular workpiece, by varying the size of the rod, by varying the shape of the rod. They observed how the constraint of the media is created and how the finishing is improved. And also they observed that when the rod is rotated at different RPMs, what is the impact of abrasive flow machining? Okay, what is the impact of surface finish and material removal rate, okay, during that rotation process? So this is one of the hybrid variant. So they worked on several materials and they claim that this particular process is giving better result compared to simple abrasive flow machining. Yeah, so another author has tried rotary abrasive flow machining. So in this particular process, so the workpiece fixture is rotated, means the workpiece is inserted in a fixture and that fixture is rotated when you are pumping the abrasive media. Okay, so you can see here they are using a one-way AFM, so one-way hydraulic action, and the other side they are using a spring loaded and a sliding disc. So once you release the hydraulic setup pressure, the back pressure, the spring will do its action. Means we have a two-way action, but the design is different. Okay, so the other side we are not using a hydraulic setup, we are using a spring loaded sliding disc. And they inserted a spindle, and this spindle is connected to a motor. So when they rotated the spindle is also connected with the workpiece. So they rotated a spindle, so the workpiece fixture is also rotated. And they pumped the media. And they observed that when you are rotating the fixture, which is inserted, merged in the media, and also we are pumping the media, so they observed some different result. So that the result is that the abrasives are having more grain density compared to simple AFM, and also they are covering the circumference of the sample, okay, and they got some uniform finishing because of the rotation of the work surface compared to simple AFM. Because in simple AFM, when you are pumping the media, we observe that several abrasive particles are inactive. Means they simply roll and slide. They simply roll and slide without cutting. So those abrasive particles we consider it as inactive abrasive particles. They simply roll and slide, they don't do that particular job. But our job is to make them more active by giving certain hybridization, like by rotating it, or by vibrating it, or by applying magnetic field, okay, or by generating centrifugal force. So there are several concepts, several things done by several people. Next, author tried drill bit guided abrasive flow machining. Okay, so in the previous case we have seen the workpiece is connected to a spindle and the spindle is rotated, right? But in this case, the author inserted a drill bit rod inside the workpiece, and then he controlled the finishing, and he named this particular process as drill bit guided abrasive flow machining. I'll tell you what is the major outcome of this process, okay? So the drill bit is inserted in a cylindrical bush, and they are pumping the media to and fro. Okay, so due to the helical fluid path of the drill bit, so the reciprocating axial flow is possible, and as well as scooping flow is possible, because we are pumping the media. So media is reciprocating, and that it is flowing on the work surface, and in between there is a drill bit. So due to the helical fluid behavior of the drill bit, there is more possible action is flowing of the media in a fluid path, axial flow, and the scooping flow. So because of these two different types of flows, they observed the material removal rate is more compared to simple AFM process. So because of the drill bit nature, okay, because of the geometry of the drill bit, so they observed more interaction. So the author tried to increase the abrasive grain density, means the active participation of abrasives on the work surface, because the major limitation is the simple AFM process is very slow, okay, low finishing rate. So they wanted to increase the finishing rate. So they tried in different ways. So one tried using centrifugal force, one author tried using magnetic field, one author tried using rotary, and one author using drill bit guided, okay. So he did not rotate a drill bit, only by the nature of the drill bit, okay, by the design of the drill bit, how it is impacting on the work surface. So next, rotary abrasive flow machining, like it's similar to the previous process, but he explored in a different way, like he has taken two-way acting abrasive flow machining, and he rotated the entire fixture. In the previous case, the workpiece is inside the media, right? So here the fixture is rotated. And the workpiece is inside the fixture, and the media is flowing on the work surface. So what happens here? So he observed that the abrasive media flow inside the work surface, how it varies by varying the RPM. Okay, so the flow of the abrasive media is controlled by by rotating the workpiece. Okay, and he also worked on the helical rotation of the work region, and how this helical motion will helps in finishing, and also how it helps in improving the finishing rate in this particular process. So he has studied on several workpieces, and several results were published, and several results are compared with simple AFM process. Yeah, so you can observe here some images which shows the abrasive scratches in helical path, and also that flow behavior, which explains that rotary behavior of the workpiece, and also the result shows about the change in RA value by varying the abrasive media and also the extrusion pressure. So we can see the trend curves of the results, how the result is increasing and then further decreasing. So another author tried spiral flow assisted abrasive flow machining. So as I said, in drill bit guided assisted, the drill bit is not rotated, right? So whereas in spiral flow, they rotated drill bit. So they rotated drill bit, and then they tried on different workpieces, and they observed that at lower RPMs it is giving a better result, the scooping action, and at higher RPMs that scooping flow is missing, only it acts as a simple rod. So they recommended at lower RPMs this spiral flow assisted will give better result compared to simple drill bit guided abrasive flow machining. And ultrasonic flow polishing. So this is the first method introduced as a hybrid method, okay, which is combined with AFM process. Okay, so the ultrasonic flow polishing is a combination of AFM plus USM. So we all know ultrasonic machining process, and abrasive flow machining also we have seen now. So when they combine these two, so what is the result? So they worked on a finishing of a blind hole. So their workpiece is a blind hole, and they targeted to finish that particular blind hole. So when they are pumping the media to and fro, so one way they are applying the extrusion pressure, and the other way the tool is designed in such a way that the media is coming out from the tool. And the ultrasonic tool is vibrated at high frequency, so the abrasive particles present in the media are excited due to this high frequency, and a small gap is maintained between the work surface and the ultrasonic tool, and due to that high frequency vibrations, the abrasive particles are acting more active, compared to simple AFM. So due to that, the abrasives are removing the work material on the work surface. So this particular process is majorly used for finishing the blind hole compared to the through holes. So next, whatever the area I worked, so ultrasonic assisted abrasive flow machining. So like in the previous case, they vibrated the media and they got some better result. And in our case, we vibrated a workpiece externally. Okay, so we vibrated workpiece externally, and we studied how the finishing is improved, and how the vibration assistance helped in finishing, and how we reached nano level finishing, and the process mechanism as well. So with vibration and without vibration, we conducted some case studies. So we worked on some application oriented materials, etc. And so those things we'll discuss few important things. So this is a setup I would like to show. In ultrasonic assisted abrasive, we used a horizontal setup, horizontal AFM setup. It is not a vertical AFM, it's a horizontal AFM. The reason is, while using this vibrations to the workpiece, so we had a better opportunity to vibrate the workpiece in horizontal AFM compared to vertical AFM. So the horizontal AFM is designed. So here we can see the hydraulic cylinders and the medium cylinders and the tooling and the piezo actuator which is vibrating the workpiece, and it is connected to amplifier, DC offset and then computer. So we can vary the frequency and also we can vary the amplitude of the workpiece while abrasive flow machining is on. Means while pumping the media to and fro, parallelly we can vibrate the workpiece. And in which direction we are vibrating the workpiece, that is important. So we are vibrating the workpiece perpendicular to the media flow direction. Okay? So we are vibrating the workpiece perpendicular to the media flow direction. And we also tried parallel to the media flow direction. So what is the effect, what is the result, and how it is better process compared to simple AFM process, those things we have discussed. I would like to show some schematics where with vibration and without vibration, so what could be the possible result. So why the finishing is better. So in the figure A, if you observe the workpiece and the abrasive particles traveling in a media, so the surface, this is the target surface which we need to finish, and this is a media flow direction, and this is the abrasive particles A. So when we are vibrating the workpiece externally, we observe that the abrasives are hitting at an angle theta. So the abrasives are traveling unidirectional when you are vibrating at high frequency, and also the abrasive force, the particle force and the resultant velocity is varying because of the additional vibrations given to the workpiece. Because when you vibrate at high frequency, which is perpendicular to the media flow direction, the radial force is increasing. So the radial force of the abrasive particle is increasing. And however, the axial force of the abrasive particle is controlled by extrusion pressure. So this is a horizontal AFM process. We could able to control the extrusion pressure as well. So now when we vibrate the workpiece at a sinusoidal cycle, okay, at a sinusoidal cycle, so we have a rising off and receding off cycle in a sinusoidal ultrasonic vibration. So in this rising off and receding off, the vibration which is inverse of time, at different time intervals, we have the enhancement of asperities, and then in the rising enhancement and then receding. So because of that, we observed some intermittent cutting action will take place, and we also observed that some abrasive particles are becoming active when there is change in the amplitude, with additional vibrations. So this is a side view of the workpiece. So this side view schematic is shown to show that the abrasive protrusions are everywhere in the circumference of the surface because of the vibration in the sinusoidal cycle, and the result is we could achieve a smooth surface finish and as well as a uniform surface finish. So this is one schematic I would like to show, like when the vibrations are given to the workpiece, like how the particle will be having a better resultant velocity compared to simple AFM. In the second schematic, the illustration is like when you give vibration and as well as at a defined amplitude, the chances of becoming inactive to active particle will increase, because at a rising off, the asperities are advancing because we are converting the electrical signal to mechanical action. So we are using a piezo actuator. For me, the mechanical action is important. I wanted to vibrate my workpiece at a defined amplitude, at a defined frequency. So when you advance the asperities, there is a chance of the inactive particle becoming active because of that advancement. And when you continue the process, then there is a chance of cutting action and also intermittent cutting. So because of the continuous sinusoidal cycle, and finally the result is the finished surface, okay, the finished nano level surface And what is our job is the major important is like whether the process is rapid or not. So that is what important for us, okay. So with finishing and without finishing, with vibration and without vibration, whether the process is rapid or not. Yeah. So this is another image which shows the tendency of abrasive heating in ultrasonic abrasive flow machining at a different T, at different time intervals of a sinusoidal cycle, how the abrasive is heating the asperity and how the cutting action is taking place and how the chips are removed and how the smooth finish is achieved, and at different events some proof is also taken, like using atomic force microscopy and as well as optical microscope. So how the sharp edge asperities were cut. So this is a nano chip cutting, you can see this small chip is cut here. So already the sample is a finished sample. We are working on to cut a microchip, a nano chip, okay, and we are working on how to have a control process for cutting nano level, okay, for cutting a nano level finish. Yeah, we tried vibrating in axial direction parallel to the media flow direction. So when you are pumping the media to and fro, we in the previous case I have shown when you apply vibrations radially to the media flow direction, and now when we apply in an axial direction, so then how the impact is, okay, at the rising of and at the receding of, how the impact is. And like based on the case study, we observed that when we vibrate radially, the result is better than when we vibrate the workpiece axially, because we are perpendicularly vibrating to the media flow direction, then there is more interaction of the abrasive particle, more radial force than the vibration in axial direction. So that's what one observation. And coming to simulation and also some case study, so we have chosen bevel gear as a workpiece. So this is a bevel gear. So we all know bevel gears are used to transmit motion for a perpendicular shafts. So bevel gear design is somewhat difficult, some intricate compared to simple gears, and we can also try helical bevel gears, right? So as of now in the case study, like we have taken a bevel gear as a workpiece and the fixture is designed accordingly. As I said, the fixture is important and the fixture design will play a role in finishing. So the fixture is designed in such a way that the media will pass on every tooth on the designed bevel gear, and also we targeted to finish a uniform finish of the gear which we are finishing. So why we studied simulation means we wanted to know the media flow behavior when we vibrate the workpiece. Okay? We wanted to know how the media behavior is changing when we are vibrating the workpiece. So we observed that the media flow velocity distribution is changing compared to simple AFM, and media flow pressure distribution is changing, and also the velocity vectors of the media which are flowing on the workpiece are straight in simple AFM process, whereas the velocity vectors are perpendicular when we vibrate the workpiece. So that is one observation. And the temperature. So we observe that the temperature is slightly increased when we vibrate the workpiece. With vibration and without vibration, there is a slight increase in the temperature of the media. So these are some of the things in simulation we observed. And some image you can see here where the boring marks, the tool feed marks which are done conventional machining processes are finished by using abrasive finishing process. Okay? So this is before finishing and after finishing. We can observe a glazed surface after finishing, and this is what I am talking about. When we apply vibration in the simulation process, we observe the velocity vectors traveling at an angle theta, and in the simple AFM the velocity vectors are traveling at an straight. Okay, so the user defined function simulation is taking place. So we used ANSYS Fluent in order to simulate the process, So where we used vibration, sinusoidal vibration, and as well as the media flow parallelly and also perpendicularly. So these are some morphology of the surfaces, and you can also see the abrasive marks and the finishing on a bevel gear. And these are some images where you can see the real fixture. Okay, so in the previous case I have shown the simulation fixture. So this is a fixture and this is a machine, horizontal acting machine, and how I am importing the vibrations and the workpiece and the schematic explaining the mechanism. Okay, so when we vibrate, so what kind of result we are going to get? Okay, in a sinusoidal cycle, so what kind of result we are going to get? So this paper we published in Machine Tools and Manufacture Journal, okay, one of the prestigious journal. So Machine Tools and Manufacture in elsewhere, I think the impact factor is more than 10. Okay, we published this work because at that time no one published in ultrasonic assisted AFM. So there is a process, ultrasonic flow polishing, but there is no process so far who vibrated the workpiece externally while finishing. Okay, so this is one result. So in the paper, one of the result we claim is to show the process is rapid. So that is important because we are working to overcome the result, the limitation. So the table shows the experimental conditions used in UAFM process and AFM process. So in UAFM, the two important parameters we added, so that is frequency and amplitude. So frequency and amplitude are the two introduced parameters in UAFM, whereas in AFM these two are zero. Okay, we are not vibrating and also we are not giving any amplitude. And coming to other parameters, extrusion pressure, processing time were kept constant. Okay, extrusion pressure, processing time, media flow rate, abrasive size, concentration, viscosity, etc. Everything kept constant, only we wanted to study how UAFM will affect and how AFM will affect. So the result shows here on the y-axis surface finish improvement and on the x-axis processing time. Processing time is nothing but number of cycles. So we convert the number of cycles in time. Okay. So and the second result shows the material removal in milligrams. We are not calculating any rate. So we wanted to see before and after how much material is removed. So we observe here the black color shows simple AFM, whereas the red color shows UAFM. So we observe one important observation here. At 5 minutes of processing time, we could reach 30% improvement in surface finish when we use simple AFM. And at 15 minutes also we could reach only 55% improvement on the surface finish. Whereas at 5 minutes itself, we could reach nearly 65% improvement in UAFM. Means within 5 minutes we could achieve more than what we achieved in 15 minutes in simple AFM process. More than that. It means that the process is rapid. And also it is increasing the finishing rate compared to simple AFM. The similar kind of result we observed in the material removal as well. So what we could not achieve in 20 minutes also, we are achieving in simple UAFM within 5 minutes. So that is one important observation we claimed. What is? Here, this is to show the slope, and how the curve, etc. So, if you see the schematic image, the SEM image and the optical microscope, we observe the deep feed marks and the rough surface on the bevel gear, and slowly the smooth surface, like after 5 minutes, 10 minutes, the smooth surface and the reduced feed marks, reduced abrasive scratches were observed on a bevel gear. And as I said, people working on abrasive finishing, which are published in Additive Manufacturing Journal, so they choose a copper tube, one of the case study, a copper tube which is 3D printed component, were studying for different finishing processes. So this is as built 3D printed components. So they evaluated longitudinal and lateral surface finish as built, and they chose the setup. This is a big setup in IIT Tirupati they have. So they choose this particular setup for finishing that 3D printed copper tube, and I would like to show the result. So they use this particular media, the galactominin abrasive media. So galactominin is one of the chemicals they use in food processing. So the chewing gum and some candies which are having that viscoelastic nature, so they are using that particular constituents, glycerol solution, and that constituents for preparing this media, and they got patent also in this. Okay, so which are flexible in nature, which are viscoelastic in nature. So they are working more detailed, like the people who are in the chemistry background and the physics background. For them, this will be the major important area, whatever based on today's session. If you can work more on constituents, you can work more on chemistry of that behavior of the media, its viscoelastic nature, synthesis of the abrasive particle, right? What kind of constituents we are using, etc. More. But as a mechanical engineer, I will more concentrate on finishing and MRR, like how this media is thermally stable, okay, what is its shear viscosity, okay, and how it helps me in finishing, etc. That is my concentration. But someone can work on this area, like how to prepare a novel media with all the properties and the functionalities which we require. So these are some of the input parameters like which I discussed, and these are some of the calculations, how the material removal is calculated, and the abrasive finishing rate in percentage is calculated, etc. And this is a same morphology of the media prepared in the case study, where we observe the abrasive particles and the base polymer, okay, the base polymer, the galactominin polymer, and the abrasive sharp edges, the polymer media and the abrasive sharp edges you can see, and like the used media, like after finishing you can see the wear on the abrasive particle, and as well as some micro chipping and also some blunt cutting edges, right? So before finishing, this is the media behavior. So you can see the separate polymer and abrasives. You can also observe that the polymer carrying these abrasives successfully, and after finishing you can see some blunt surface on the abrasive and the micro chipping and cutting edges, blunt cutting edges, etc. like after finishing. And after finishing, of course, you can also see the metal powder. So the metal powder is also mixed along with the media. Yeah. So as I said, the TGA analysis, thermogrammetric analysis, FTIR analysis, I think in the Professor Harinath sir has explained about several characterization techniques, right? So for a non-metals, for a polymers, if you want to study in detail about its behavior, its main constituents, and time versus temperature, how it is behaving, so that is one kind of study you can do. So in this particular process, whatever we are discussing today, we'll have some laboratory session as well along with the 3D printing lab. So people who are interested can work more on the media behavior, okay? So majorly thinking about what kind of requirements we need, what kind of behavior is in detail about that, okay? But we study more on finishing and mechanical things, but the participants may discuss more on the chemical and the chemistry and physics behind the media, okay? So the TGA analysis and FTIR analysis to know the main constituents, and coming to the results. So they were looking after the number of cycles only. So at the number of cycles, how the finishing is taken, you can observe the layer by layer printing of the component, and by applying pressure, how the finishing is taking place. And you can also see the surface morphology with respect to different cycles, like 50 cycle, 150 and 250 cycles, and how the final finished surface looks like, and how the before surface looks like, okay, as a 3D printed component and then finished component. And effect of every parameter is discussed. So to know the media flow direction, and also to observe the layer thickness, and as well as mainly targeting on how the finished component, okay, as built component and finished component. And the abrasive size is also proved with SEM image, like what kind of abrasive size is used, so abrasive scratch marks, deeper indentation, and if any porosity observed on the finished surface, etc. are identified. And developed media with other media. So as I said, there are two research majorly working. One is hybrid AFM. So people trying using different hybridization like magnetic field assisted or rotary or drill bit. Okay, that is one area. Second is using different types of media. Okay, so some people in the literature they used gum based media, some GUR based media, some SBR means that synthetic based rubber, okay, natural rubber, and galactominian media. Some used natural polymers, some used wax, okay, some used honeybee wax. So like that they use different types of media, and several people got patents and better results in their different media they used. And the mechanism you can see here. So the abrasive particles traveling in the work surface, and schematically whatever the observation in the SEM image, explaining what kind of machining is taken place, like rubbing action, micro plugging action, okay, and the shearing action of the abrasives. So all this we need a proof, right? So the proofs are explained with the help of SEM images. So the mechanism is explained with the help of a SEM image. So this is a possible rubbing, this is a possible rubbing action, this is a possible finishing region. So this is as built, etc. And now we are working on rotary ultrasonic. As I said, during my PhD I worked on ultrasonic assisted AFM, and in the literature we can see rotary, right? So when these two are combined, okay, when the rotary technique, rotary assistance, and also ultrasonic assistance is combined. So this is our ongoing project we are working on. Okay, the name of the project is Rotary Ultrasonic Abrasive Flow Machining. So when the two effects are given, how the results? Okay, this we got under core research grant DST, and we also using ultrasonic this one acoustic emission. Okay, we are using one sensor to find out the online monitoring of the abrasive media. Means we wanted to know, we wanted to predict the surface roughness. So we wanted to know when to replace the media, or when to stop the machine, we wanted to know the information like when we reach our required desired area. Okay, something like that. We are using the sensors. So this sensor is fixed to the workpiece, and then it will continuously monitor the media flow. So there is another variant called chemo-mechanical abrasive. So we are working on this. We started to work on this. So in this particular process, the chemicals are used. Okay, so it's a combination of chemicals. So you can see here the abrasive flow machining we are pumping to and fro, and there is a injection of oxidizing agent inside the tooling zone, and there is a heating system. So how the chemical agent, oxidizing agent we are using, and how it reacts under different temperatures, and the fixture design for that, right? And basically if you see the working principle, so the abrasive media and the substrate and the diamond film, the oxidizing agent. So how this oxidizing agent helps in finishing. So we are working on that also. So there is a lot of scope in finishing dental implants which are complex in nature, and medical implants which are complex in nature. And to see the overview of the parameters, like in the simple AFM, machine based, media based and workpiece based, we Whereas in hybrid AFM, we have magnetic flux density and current in magnetic assisted, and shape of the rod, rotational speed in centrifugal force assisted, and drill diameter in drill bit guided, rotational speed of the workpiece in RAFF, current intensity and voltage, abrasive paste, etc. in electrochemical, and also there is a chemo FM. In UAFM, the application of vibration speed. So these are all the new parameters introduced in the field. Okay, so I would like to stop here. So in the laboratory session, you can see the setup and how it is functioning, okay, and how we prepare the media, right? So, and also 3D printing lab possible. 3D printing lab is possible to see. Shobhan? Yeah, so we can also see the 3D printing lab and as well as this abrasive flow machining lab in the today's session, okay? After lunch we have a session from Professor Vamshi, and after that this lab visits we can plan for today, okay? Mostly tomorrow 2 sessions we have, so that we'll discuss, okay? So now this session is open for the questions. So majorly the people from the mechanical background. So those who want to work in this area, you are welcome to discuss, not only now, later also. So you can see the laboratory arrangements, and if you want to collaborate or if you want to do some work in case of developing a new media, okay, because everyone will have different ideas. So one author tried galactominnan polymer, I tried natural polymer, some other tried rubber based polymer, like that. Some media with different properties which match our application, probably you can look into that. And mechanically also, if you want, like my project is based on rotary and ultrasonic, someone may think in a different way if you see the literature. If something like that, you can always collaborate with us. Okay. We'll end this session by this. Okay. Thank you all. Yeah. Yeah. So the temperature in abrasive flow machining is not more than 70 degree. Okay, that's why it's not much affecting on the material. Okay, because the abrasive media, which is with the help of thermocouple and also in the literature, it's not more than 70 degree. So that's why there is no effect on the work surface. Material properties are not going to affect because it's working under lower temperature only. The machining is taking place at lower temperature only. Still any? Still any questions? Reusability of the media, yeah. So in one of the patent, the author used a honey bee wax, and after machining, he melted the media and he has taken out the wax, removed the abrasives and reused it. So that is one claim. So reusability can be possible only if you can do this, such things, okay. Reusability is not possible for rubber milk or any other medium. Now we are using silicon carbide abrasive button. Mesh size, we have 4 or 5 mesh size, okay, 120, 80, 180. Sorry? Yes, exactly, we can do that. Commonly used 180, I think, 180 mesh size. So if the abrasive mesh size increases, then the particle size decreases, right? So higher the mesh size gives better finishing, lower the mesh size gives better MRR. So we need to optimize. So optimization requirement is there. So during my study also I have optimized all the parameters. Yeah, you can think about it. We have not done in that particular, but what are the results you are expecting, that is important. So we have not tried that. But if you have any idea, then no one has tried in the field. You can look into that, those things. Okay? So cryogenic EDM you have seen, but AFM so far no one tried. They are doing. Probably you can see our environment, the working environment here. If you suggest something like, means, but there should be some reasoning also, like why cryogenic? Yeah. The addition of this cryogenic setup has increased the efficiency of the machine. So that we will discuss in the lab. Okay. If any possible solution is there, that we can try. So, any other questions? Okay. If no questions, so we can meet at 2:30 again after lunch. ముందు దిగేసాం చాలు.
Application of solid lubricants in machining process, application of eco-friendly nano-cutting fluids in machining, vibration-assisted machining, modeling and simulation of manufacturing process and composite materials. 5 students were awarded PhD and 5 are pursuing PhD guidance under his guidance. He guided 35 postgraduate and 19 undergraduate projects. He completed 5 funded projects and 1 is ongoing. He published 1 textbook, 3 textbook chapters and edited 3 books. He published more than 130 research papers in reputed journals and conferences and 1 patent. He is editorial board member for 10 journals and delivered 35 guest lectures. He is recognized as one of the top 2% most influential scientists in 2022 Stanford University list. He is awarded with Outstanding Reviewer Award by Tribology International Elsevier in 2017 and Best Reviewer Award from Transaction of Indian Institute of Metals in 2020. And now I welcome Professor P. Vamsi Krishna sir to please come on the stage and start with the presentation on the topic nanomaterials for cooling and lubrication. Please have a big round of applause for sir.
This is mostly related to mechanical engineering because it is based on the machining process. Okay. So how we use these nanomaterials in the machining process as a lubricants and coolants. That is one case study I will take and I will explain. So here I think already you have gone through different lectures. Already you know what is nanomaterials, nanoparticles and nanopowders. I need not explain. But anyway, so normally here we consider any of the zero-dimensional nanostructures which are having less than 100 nanometers is considered as a nanoparticle or nanopowders. So then here the next class is nanofluids. That means if you use these nanoparticles or nano powders to prepare a fluid, then we can call it as a nanofluid. So that means we have a base fluid like any of the oils or maybe water or some other alcohol or glycides, etc. Then we take some nanoparticles and we mix these nanoparticles into the base oil. Then we prepare the nanofluid. So this nanofluid normally we use in different applications, like as coolants in radiators or maybe heat exchangers or in different applications. But here we consider this as a cutting fluids. So this is what we consider here, we use as a cutting fluids. So normally we take different nanoparticles, that is like carbides, metals and their oxides, or maybe carbon nanotubes, and we mix into different base oils, then we prepare the nanofluids. So as you know, already you studied about the basic things about these nanoparticles, like which are having more surface area, right? And also very small particles, and we can able to mix more number of particles into a small quantity of the or small weight of the material gives large number of particles, right? So before going to this application, first we should understand why we require this nanofluids in the machining, right? So that is what very important. So all of you know, right, of course you may or may not be having the background of mechanical engineering, but it's okay. So we manufacture many of the components by many processes, right? So if you take this table, we manufacture by some process, or if you take any of the thing, this fan or AC, everything we manufacture by different process, right? And also each product is not a single component, right? So if you suppose you take this pen, this is a combination of so many individual components. So we have this button, cap, bottom and inside refill, right? So ink, everything is there. So what we can do is we manufacture the individual components and then we assemble these components to get the required functionality, that is nothing but a product, right? So and also all these components we manufacture by different process, like casting process or welding process or maybe forming process or machining process, and nowadays we are using additive manufacturing, etc., etc. So basically in machining process we manufacture number of components, right? So this is a majorly used process in any of the industry, okay? So machining is the majority of the cases we use the machining process. Like for example, you want to make the door, right? So we can take a wood and we cut the wood into required dimensions, and then we give design and we give finish, etc., right? So similarly, any of the things, if you want to make a holes into that wall, then we use a drill bit, okay? Like that we use machining for many of the applications in many of the cases, okay? So in this machining process, actually what is our final requirement is, any of the product what you are manufacturing, that product quality should be good. But how can you define a quality? It depends on the product, right? Suppose you take your two-wheeler, then how can you say the quality is good? Depends on the mileage and depends on the stability, right? And depends on the safety. Or if you take your four-wheeler also, same thing. How much mileage you are getting, and if any accident is happened, what is the safety, and also what is the lifetime, etc. Like that, if you take any of the product, the quality is different, Suppose you take your AC. So how can you say the AC quality is good? Plus power consumption and also the lifetime. How many years we can use this without any problem? So sometime we use 5 years, sometime we use 10 years, or sometimes maybe we can use 20 years also, right? So if you see, maybe nowadays if you think about TVs, right? Previously in olden days, if any repair we are getting to the TV, we can replace that component. But nowadays we have to change the total component because we are getting a integrated picture tube, everything. So the lifetime may be less, even though the quality, the picture quality is good, or you are getting a bigger size, etc. But the lifetime may be less. Like that, depends on the product, the quality of the product is different. Sometimes we can say the quality good means it may be a lifetime, it may be a power consumption, less power consumption, it may be a look. Suppose you are purchasing some chain, gold chain or earring, then how can you see? So maybe appearance is good, right? So then we require good design, good finish, etc. So like that, in machining process, if you are manufacturing any product, then the quality is important. So here the quality means normally what we consider is the dimensional accuracy. Why? Because we have to assemble the individual components. If the dimensional accuracy is good, then only we can assemble these components. See, you can see sometimes maybe if you purchase a pen, after a few days itself the cap may be very loose. Okay, sometimes the cap may be breaking, right? You observe that one. So maybe if you know the Montex pens, the transparent pen, very drawback is the cap is easily breaks, even though the quality of the refill, the pen is good. So like that, what is happening here? Because of the dimensional accuracy is not good, then we are getting failure of the component. So we required good dimensional accuracy and the surface quality also. Sometimes we required a better finish, right? If the finish is not good, then also the friction may be more, and then we lose the product lifetime, like that. So normally in machining process, what we consider is, if the dimensional accuracy is good and the surface quality is good, then maybe the quality of the component is good, individual component is good. Then like that, if you assemble number of components, the final product functionality may be good. Because if the number of components quality is good, then only the functionality is good, right? So sometimes you can purchase a cooker, right? So in the cooker everything is good, maybe for example it looks good, the quality, everything, but if the safety valve is quickly damaging, you observe that one with some type of models, right? Quickly it damages, right? Then we have to replace it, like that. So in each product, each component is good, then only the quality is good. Okay, right. So now we consider in the machining, normally, generally, the dimensional accuracy should be good, surface quality should be good, and the total manufacturing cost should be less. Then only the process is efficient, right? Okay. So now we see why when the surface quality is good. So we can say this one in two types. One is the finish may be good, or the finish reciprocal word or word is rough. So if the finish good means roughness is less. If the roughness more means the finish is less. So we use these two words simultaneously, don't confuse. So here in any of the machining process, this surface finish or surface roughness is depends on number of factors, like That is, the first one is workpiece material. So what type of material we are machining? It may be wood, it may be aluminum material, or it may be steel, or it may be cast iron, or it may be some other hard materials like tool steels or alloys, etc. And sometimes this also depends on the cutting conditions, like we are running the machine at a higher speed or at a lower speed, or sometimes whether we are giving more depth of cut or more feed or not. That is nothing but, for example, you are running a two-wheeler, like you take a small Activa. So if you are running that Activa maybe at 40 kmph or 50 kmph, it may go smooth. But if you go beyond 70 or 80, you feel that vibrations, right? Of course, it also depends on the road condition, right? And also weight of the person. Okay, like that here also the machine also depends on, the machining also depends on the speed at what we are running the machine, as well as how much amount of material we are removing, like that. And then other one is tool variables, that is what type of cutting tool we are using, whether the tool condition is good or it is worn out, that is it is a blunt tool or it is very sharp, like that. And other thing is the lubrication condition. That means whenever the machine is running, right, so then the heat will be generated, right? All of you familiar with this one. If you rub any of the stone on the surface also, you can feel that heat, right? So like that here, when you are cutting the material, the heat will be generated. So that heat will be transferred to the cutting tool as well as the workpiece material, or that is nothing but the product. So for that reason, to reduce the heat generation as well as already heat is generated, to remove the heat we require the lubrication and cooling action. Okay, so that is what this lubrication or cooling is going to influence the machining process. Okay, so that is like maybe we use the lubricant as well as coolant in your vehicle also, right? So the lubricant is used maybe to run the different parts of the engine smoothly, but at the same time the coolant is used to cool the radiator or engine, like that. So like that, similarly in the machining also we want the cooling action as well as we want the lubrication action. Okay, we will see here why we required both. That is what important thing. So actually this is the cutting process, like we have the cutting tool here. So the tool is cutting the workpiece material like this. So here the chip formation may take place. Okay, so what is happening is, here there are three zones. This is one zone, this is other zone, this is the third zone. So we can say this one is a primary deformation zone, and this is secondary deformation zone, and this is a tertiary deformation zone. So what is this primary deformation zone is, here the chip is removed from the material, right? It's nothing but simply you remove the skin of a banana or skin of any fruit, like that. So we are removing some amount of material from the workpiece, but with the help of a tool, where sometimes you use knife, similar to this one. So then what will happen is, here in the primary deformation zone, actually what will happen is, there is a elastic plastic deformation. Because of that one, the heat generation will be there. So what is this elastic plastic deformation, right? So for example, I want to move this stool, right? So if I apply a small force, for example with my single finger, I may not move. Why? Suppose this table is there, I want to move it like this. So simply if you apply a small pressure, you cannot move it. Why? So it offers resistance. It is having some weight, right? So we cannot move that. So but if I apply more pressure, then I may move it. Of course, if I apply more pressure also, I cannot move this one. There are conditions applicable. But for example, you take any chair of that single chair. If I apply a small force, I may not lift it. But if I apply more pressure or more force, I may lift it. Why it is not moving initially? Because there is a resistance from that chair that is nothing but depends on the weight of that body. So if whatever force I am using is more than that, then only I can able to lift it. But similarly here, any body has its internal energy and bonding strength, right? So if I want to cut that material, it offers resistance. Okay. So if the force applied by us with the help of a tool is less than the resistance offered by this material, then we cannot cut that material. If the force applied by us is more than the resistance offered by that material, then only we can able to cut it. So what will happen is, once the force is more than the resistance offered by that one, then also the material is taking first elastic deformation. Are you studied stress strain diagram of metals? Maybe even though if you are not mechanical engineering, in the first year BTech you studied about that one. So if you see that stress strain diagram, right? So it is going like this and like this. So up to certain level, it is a straight line. That means stress and strain are proportional. It's nothing but that region is called elastic region, and then plastic region, and then the fracture takes place. So here also same thing. What will happen is, if we apply a force, then it will deform elastically. Do you know what is elastic deformation? If you take a small rubber band, if you apply a pressure or force, and if I leave it, it comes to the normal state. That is nothing but elastic deformation, right? But if you take something else, then if you are applying pressure and leave it, maybe you take roti, making of roti, chapati, right? Then if you apply a pressure, or you can apply a pressure, it will spread. If you remove the pressure, it will not come back. That is plastic deformation. Okay. So any material, if you apply a load or force on that one, initially subjected to elastic deformation, and then plastic deformation, and then fracture takes place. That means separation of the material takes place. So that is what happening in the primary deformation zone. Okay, right? So then after the chip is formed, it will flow like this on the tool. That is the rake surface of the tool. So when the chip is moving on that one, again here, because of this surface which is having some coefficient of friction, so all this tool and chip are subjected to friction, I mean rubbing action. Okay. So again here also, in this total region, up to certain extent it is called as sticking zone, and some part is called as a sliding zone. That means the first half is having high temperature because the material is just separated from the raw bulk material, so which is having more amount of heat, and which is at a high temperature, and then the second half is a slightly low temperature. So that is why at high temperature the metals are having the nature of welding, right? All of you know welding. So how can you weld? You can heat the metal and then joining. So same thing here. We are not heating, but intentionally we are not heating, but because of the process, the temperature is high and there is a temporary weld takes place between the chip and the cutting tool. So then it is called as sticking zone, and then we have a sliding zone. So here, because of the friction, then here we have only plastic deformation, because this material is already subjected to elastic deformation and shearing takes place. Then there is no elastic deformation, it is having the plastic deformation and then friction. Because of these things also the heat generation is there. So in the primary deformation zone, the heat generation is because of the cutting of the material, that is separation of the atoms and molecules or bonds. And in the secondary region or secondary deformation zone, the heat generation is because of the rubbing action and because of the coefficient of friction. Okay. And then coming to this tertiary deformation zone, then the tool surface is maybe slightly touching on the already machined surface. So then because of the coefficient of friction, again there may be a little heat generation is there, right? So in the primary deformation zone, the heat generation is because of the material property, okay, that we cannot change, we cannot stop it, because if any material you are cutting, there may be, you require some energy and there is a bonding strength between the atoms or molecules or something, and then it generates some heat that we cannot change because that is a material property. But in the secondary deformation zone, if you are able to reduce the coefficient of friction, then maybe you can reduce the heat generation. And if you are able to manage the sticking and sliding nature of that surface, right, because already it is at high temperature, so if you are able to cool it quickly and if you are able to reduce the coefficient of friction, then what will happen is we can able to reduce some amount of heat in the secondary deformation zone, as well as the same we can able to reduce heat in the tertiary deformation zone. So what we understand here, to reduce the friction we want lubricant, okay, and already heat is generated in the primary deformation zone. So to cool that tool or chip or whatever heat is generated, that you have to remove quickly, so that we can able to reduce the coefficient of sticking and sliding nature. So that is why in any machining process, I am showing here just example of single point cutting tool, but you take any machining process, it may be drilling or it may be shaping or milling or any process, when you are cutting the material, the heat generation is there and we require the coolant as well as lubricant, that is to reduce the heat generation in the secondary deformation zone as well as to quickly dissipate the heat generated in the primary deformation zone. So why you have to reduce this heat generation, or why you have to quickly extract the heat generation? If you don't reduce the coefficient of friction, or if you quickly don't dissipate the heat, what will happen is the tool will be damaged. Because of high temperature, the tool will be damaged, and also because of this chip formation, sticking action and here, the total workpiece quality may be slightly damaged. So why tool is damaged? You know, any metal, if you heat it, the strength of the metal is going to decrease. That is why sometimes if you are not able to bend it, we can heat and bend it. Am I right? All of you know. So similarly here, when the temperature is increasing, the strength of the material is going to decrease. So the strength of the tool is decreasing. Of course, strength of the workpiece also decreases, but here the tool is there in the machining zone, and also the volume of the tool is, or the area of cross-sectional volume of the tool is very less compared to the workpiece. That is why the tool will be more affected, and then it is subjected to tool failure. So which obviously damages the quality of the workpiece as well as dimensionally and surface quality, etc. So that is why in any machining process we required the cooling and lubrication action. So normally we, of course, this is what already I told you, tool wear is there. Tool wear means the tool failure will happen. So because at high temperature the material loss taking place because of the diffusion, because of other phenomena, so the tool failure may happen. So that is why in any machining operation we use a cutting fluids. Okay. So the cutting fluid function is, it should act as a coolant as well as it should act as a lubricant. Okay. So, but what is this cutting fluid? Sometimes we use only water, but water is a good coolant, but it is not lubricant. The viscosity of water is almost zero, right? Otherwise, then if you take any of the oil or grease, etc., so then if you are applying oil, it is a good lubricant, but it is not a coolant. So if you want both cooling action and lubrication action, means we want to mix water and oil. So we mix water and oil, but normally, you know, if you drop some coconut oil or something in water, it will not mix. Why? Because H2O molecule is stable, right? And the structure of these oils is different, so which will not mix. These are not solvent. This is not solvent. So then what we can do is, actually here we use some chemical or which is called as a surfactant, right? So into this one. So what will happen is, this surfactant will break the H2O molecule into H plus and OH minus ions. So once this water molecule is breaking into H plus and OH minus ions, it is not stable. The lifetime of this one is very less. But once you break that one, this H plus and OH minus ions, then only these ions will mix with any of the oils, and then it gets like a solution, and then it is having both cooling and lubrication property. So that is why in the conventional cutting fluid, normally we mix water and oil and a surfactant. So we prepare the cutting fluid, and normally we use that cutting fluid in any of the machining operation. So this is what in the olden days, that is basically. But after that, everyone realized that these cutting fluids are not eco-friendly. Why? Because, you know, suppose you see in the drainage, right? Normally in the drainages, what will happen? Many of the mosquitoes will be there. So many any of the disinfectants are there. I mean, infectants are there. Many microorganisms will be developed, etc. Right? So why? In the drainage also only water only flowing. But not only water, we are leaving so many things into that one. Maybe whatever we use in our bathroom or cleaning of our house, etc., etc., everything. So there will be a detergents, there will be so many oils, etc. So that is why in the drainages, the water molecule is going to break, and which is not stable. That's why it is the origin for so many things. Okay, so many microorganisms will be developed, and biocides like that. So many chemicals will be there. So actually what will happen is these are going to create environmental pollution, right? That is why actually many of the chemical factories, if any of the chemical factory waste, if they mix into any of the river or water, the water will be polluted. Even it is simply leaving to the outside, then the soil also polluted. You cannot go for the cultivation near to that one. Why? Because the same thing. So many chemicals are coming out. Again, water and these chemicals are mixing, and which will not be environmental friendly. So these disposals are creating diseases to the workers and spoils the air, spoils the water and soil also. So we cannot use the water, we cannot use the air, and we cannot use that soil for cultivation, etc. So all these are the drawbacks. Of course, the cutting fluid amount is small, but the effect is similar to this any of the chemical factories or pharmaceutical factories, etc. But there is a factory, so then the volume is more, so we can see the effect quickly. But here with cutting fluids we cannot see, but the effect is the same in a longer period. So because of this one, normally the research is towards eliminating this conventional cutting fluid. So then what are the alternatives? So then we have these are the environmental effects of cutting fluid, that is what already I told you, right? So then what are the alternatives to this cutting fluid? There are so many alternatives, like we can use cryogenic, so which we cool the machining environment at very lower temperatures, and then we use a solid lubricants. So you know cryogenics, right? Maybe liquid nitrogen or something at very low temperatures, so that the heat will be dissipated very quickly. That is advantage. Cooling will be better. And we use solid lubricants. Do you know what are the solid lubricants? Graphite or boric acid or molybdenum disulfide. Like that, there are so many solid lubricants. All of you know, maybe at least all of you know boric acid. Can you tell where we use? Yeah, we use powder on the carom board, that is boric acid. Why we are using that? That is same to move the striker freely, that is to reduce the friction. That means it is a good lubricant, right? So like this we have different solid lubricants to reduce the friction, but here the cooling action is not there. We have a lubrication property good, so the cryogenics are having one good property and solid lubricants are having one good property, but both the properties are not there. And then we have vegetable oils which are extracted from plants or vegetables, where these are good for biodegradability, right? We don't have any issue like with petroleum based oils are not good, but however the vegetable oils are good. But at the same time the vegetable oils are having more viscosity, right? Maybe acts as a good lubricants but not be a coolant. So then we have another concept of minimum quantity lubrication in machining. That means we use the cutting fluid or maybe oil or something, but in very small quantity, so that we can able to reduce the pollution. Because in the conventional cutting fluid, maybe per 1 minute we can supply some 500 ml of cutting fluid, like that. It is a flat coolant. But here in MQL, maybe for 1 minute you can use 5 ml or 10 ml, like that. But what we are doing is in MQL, we are mixing this cutting fluid or oil into air along with a compressed air, and we are sending into the machining zone. So it's like a spray, so that it will be better effective even with low quantity, right? That is one advantage. And but what is happening is, again, in the minimum quantity lubrication, there are drawbacks is the quantity what we are sending may not be sufficient for cooling action. May be sufficient for lubrication sometimes, or sometimes may not be sufficient. Then by seeing all these things, the other category is nanofluids. That is what one of the alternative to the conventional cutting fluid, to avoid all these drawbacks and also to get both lubrication and cooling effect, people are used nanofluids, and the research is going on, right? So then from the nanofluids, again the hybrid nano cutting fluids also evolved, right? I'll tell you what is hybrid. So these nanofluids are used in along with the minimum quantity lubrication, so that the quantity is less and the nanofluids we are using. But why nanofluids are useful even though at minimum quantity is, already maybe you might be knowing based on the previous classes. So these nanofluids are having high thermal conductivity, right? Are you know? Not. Because in the base oil we are adding nanoparticles. So the solids are having the more thermal conductivity. So because of the mixing of this one as well as high surface to volume ratio, etc., then we are having high thermal conductivity, right? And also we are going to increase the viscosity, right? And also if the nanoparticles what we are using are again a solid lubricants, then we get the lubrication action also. Like that, by mixing different nanoparticles, we get advantages of this lubrication, cooling, etc., compared to the other alternatives, right? So this is what actually the application of these nanoparticles or the nanofluids in the machining. So then making of these nanofluids, so people are using so many different types of nanoparticles like Al2O3 or TiO2, SiO2, SiC, etc. So these are all, some are metal oxides or metals or non-metals, etc. And also people are using carbon nanotubes, that is again single wall carbon nanotube, multi wall carbon nanotube, etc. So all these are nanoparticles are mixing into a base fluid. So that is again we have two types, two methods, in the one step method or two step method. In one step method, directly we go for a chemical reaction and we prepare the fluid that itself contains the nanoparticles, and in two step method we prepare the base fluid separate and nanoparticles separate, then we mix. Okay, that is a two step method. And the next one is hybrid nanofluids. What is this hybrid nanofluids? In the nanofluids, normally we mix any one type of nanoparticle into the base fluid. But if you mix 2 or 3 different nanoparticles into a nanofluid, then it is called as a hybrid nanofluid. Why? Because for example you take some metal. So these metals are having high thermal conductivity. So if I take CuO or TiO2, etc., if I mix these metal oxides into any of the base fluid, then the thermal conductivity will increase. But that means if the thermal conductivity is more, it is having the more capacity of absorbing the heat. Okay. But what is happening? The lubrication may not be good. Of course, the base fluid is having anyway, has its own lubrication. Suppose I want to improve the lubrication also. Then if I mix a nanoparticles of solid lubricants like boric acid or MOS2, etc., this type of solid lubricants if I prepare as nanoparticles and if I mix that nanoparticles into any of the base fluid, then what will happen? The lubrication will be good. Why? Because these are the solid lubricants as well as already base fluid is having some lubrication capacity. So it will be good. So if I want both, Then I will take some both the nanoparticles and I mix both the nanoparticles into the same base fluid. But how much percentage we have to mix? And then the stability of the nanofluid is also very important. So that's why we have to check all these things. So we take vegetable oils, right? Why? Because again vegetable oils are biodegradable. So that's why we take vegetable oils. And normally these vegetable oils are having fatty acids which are normally two types, saturated and unsaturated type. So this saturated fatty acid contains all single bonds, whereas unsaturated fatty acids contains a double bonds. Why? Because the strength of this fluid, base fluid, depends on this either it is having only single bonds or double bonds, as well as and also depends on the length of the bond, that is between the carbon atoms. That is the length of the carbon chain is different in different fatty acids. So for example, if the less than 8 carbons are present in called as a short chain fatty acids, or from 8 to 14 carbons it is a medium chain, or maybe 16 or more carbons contains a long chain fatty acids. So like that what vegetable oils we are taking, whether it is saturated or unsaturated, and what type of fatty acids are there, and also and what type of carbon chains are there, whether it is long or medium or short, like that, based on this combination also the stability is going to change. So then like this, if you see this is one just example case study. So if you take 3 vegetable oils, right, sesame oil, mahuva oil and neem oil, then these are the properties of vegetable oils, that is iodine value, pour point, cloud point, and kinematic viscosity, flash point and density. So here one more property we required, the flash and fire point of this vegetable oil should be high. Why? Because the temperature is high in the machining process. So if the flash and fire point are less, then there may be a chance of burning or maybe quickly losing its properties. That's why we required more viscosity, more flash point and fire point, etc. And then if you see the chemical composition, here we can see each vegetable oil has some percentage of saturated fatty acids and some percentage of unsaturated fatty acids. So you can see this one, this is palmitic acid, stearic acid, oleic acid, linoleic acid and linoleic acid. So normally we consider this one is more important for the cutting fluids. Okay, in this application we consider oleic acid, so that what will happen is the structure may be like this. Okay, so it is contains mostly single bonds. So we have saturated fatty acid, and the length of the chain is also important, right? So then selection of the nanoparticle, right? So here also we have a lot of availability is there. Then depends on our application we select the nanoparticles. So here I want both cooling and lubrication. So normally among the available nanoparticles, C and T's are having the high thermal conductivity. So if I take C and T, then I can able to get high thermal conductivity, so that it acts as a better coolant, right? So it absorbs more amount of heat from the machining zone. And then if I take MOS2, this is one of the solid lubricant. Of course we have different types of solid lubricants are there. Among that solid lubricants, MOS2 is the one of the better one. Better one means it withstands high temperature, right? And also the coefficient of friction is less, so that the stability is more. So why it acts as actually solid lubricant is, actually if you see the structure is like this. Okay, so this is like a one plane, this is other plane, this is other plane, this is so between the planes the bond is very weak. But within that plane, the bond is very strong. So, if between these two surfaces, if you are keeping this solid lubricant, when you apply like this, it will slide very easily because the top layer is sticking to the top body and the lower layer is sticking to the lower body, so that the sliding action is very easy. That is why it creates a low coefficient of friction between the two moving bodies, right? And then this CNT is having maybe single wall or double wall or multi wall like that. So these are having a fullerene like structure like this, right? So then if we mix these two, okay, there is a possibility of getting both better lubrication and cooling action. So that is why, suppose if we are selecting this one in one application, and then before going that we need to understand one more thing, nanoparticle functionalization. So what is this nanoparticle functionalization? So directly we cannot mix the nanoparticle into all the fluids, all the things. Why? Because here some of the materials are hydrophobic materials. So what is this hydrophobic material? Anyone know? Huh? So this hydrophobic material, it's nothing but it reacts with water and maybe it acts as a solvent. That means actually here what we want is the nanoparticle should not solve into this base fluid. It should be like a suspension. Okay. So if it is solving into that, it loses its properties. So it should not solve into that one. But if it is hydrophobic nature, then there is a possibility of solving this nano material into the base fluid. That is why we can check that one, and then we can go for the functionalization. That means we change that nature. So the nanoparticle surface is functionalized like this. Okay, so we use AG, and then we make the functionalization. There is a process for functionalization. So then what will happen is, every nanoparticle is formed like this. The surface is functionalized with some other material, right? Then it will not solve into the base fluid or solvent. So here this is the nanoparticle functionalization procedure. That is we use H2SO4 and HNO3, and we repeat, we wash this one into that procedure is there. Then we can wash it through this mixer, reflux it, and then we can go for filtering, and then we dry it. Like that we change the surface nature of this nanoparticle. So these are called functionalized nanoparticles. So basically the CNTs may be having that nature of the hydrophobic, right? So that we can go for the functionalization. So that we check the XRD, that means after functionalization any properties are changed or materials are changed, etc. So and we have to ensure that it is still as a CNT. There is no chemical reaction between the functionalized materials and the original nanoparticles. Okay. So then we can form a nanofluids, that is these functionalized nanoparticles we mix into base fluid in a two-step method, so that we can make a nanofluid. That is what, so we take a base fluid like this, and then we mix nanoparticles into particular ratio, maybe 1%, 2% like this. So we use the ultrasonicator, so that otherwise we cannot mix normally, because nanoparticles cannot mix normally because of high number of particles. So we use the probe type sonicator or maybe bath type sonicator, etc., anyone, so that it rotates with a high frequency and high number of rotations, so that we get this one. And then like this we prepare the nanofluid, and this is the one, while preparing this nanofluid or hybrid nanofluid, so how much amount we have to mix, that is what important. So here the base oil we took 3 base oils because we don't know which combination works better. So based on the basic properties of the vegetable oils, we took 3 base oils, that is sesame oil, neem oil and moho oil, and then we took 3 surfactants, right? Because the surfactant also required, because sometimes we cannot mix the nanoparticles completely into the base fluid. So that's why we took 3 surfactants, Triton X100, SDS and Tween 80. Of course these are selected based on the literature. Okay, of course that is already these base oils, vegetable oils are used in different applications, right? May not be this one, but different applications. So there people studied what is the structure, what is the percentage of fatty acids, etc., etc., and like that we get the literature on the each vegetable oil. And similarly we got properties of surfactant also. So based on their properties we selected these things, and then we use the concentration of surfactant in terms of percentage of nanoparticle weight. So how much surfactant we have to mix? So that's why we took 3 percentages, that is 5% of the nanoparticle, 10% of the weight of the nanoparticle, and 15% of the weight of the nanoparticle. And then we used this hybrid ratio, that's what I told you. We took 2 nanoparticles, CNT and MOS. So again there is a question, whether we have to take equally or not, or any other ratio, that we don't know. So that's why we selected 3 ratios, 1:1, 1:2 and 2:1, right? Of course we can try other ratios also, just we took this one. And then there are so many combinations, so we don't know which combination works well. So we took orthogonal array experimental design, and then we prepared a number of trials, and then this is actually calculation of concentration of nanoparticles, that is weight of the nanoparticle by weight of the nanoparticle plus weight of the base fluid, that gives the concentration of a nanoparticle, right? And like this, after preparing all these nanofluids or hybrid nanofluids, we have to check the stability, right? So stability means whether these nanoparticles are mixing properly or not, and also after a period of time whether the nanoparticles are suspended or coming down as a sedimentation, right? That is what we need to check. So that maybe you can see visually and you can check, but sometimes the visual inspection may not be suitable. So for that one normally we use a zeta potential value. So for that one we use this type of nanoparticle analyzer is there. So if the zeta potential value is 0 to 30, then this nanoparticle or this nanofluid is unstable. Or if it is 30 to 40, then maybe moderately stable. Or if it is 40 to 60, it is stability is good. Or if it is more than 60, then we can say excellent stability. So after preparing this one, then we can check with the analyzer, then we see what is the stability of this particular nanofluid. If the stability is not good, then maybe we can try with other percentage of mixing or other surfactant, etc., right? So then these are the tests, right? So this is a sedimentation test. This is after 156 hours. If you observe before going for zeta potential test, just we observe that one, right? So this is what we observe. So some are the particles are coming down and making at the bottom, right? Sedimentation is taking place. So then like that we can observe, so that so here if you observe this one, more sedimentation is there, and here no sedimentation, here also moderate sedimentation is there, and here also no sedimentation. But sometimes even though the sedimentation is not there, sometimes we observe some bubbles or some type of reaction, etc. So which may not be suitable for our cutting fluids, right? So then after that again we verified that zeta potential values also. So where we got a high zeta potential value, that is more than 60, then we got these two are higher values, and again we have some negative values and we have some positive values. Both are okay, right? So then we took these two, right? Of course this is also having the higher value, right? But why we are taken this one is here the base oil is different and this is sesame oil, so where we got the better value. So that's why we took that combination, right? And then we tried different things like different percentages, different surfactant, etc. Then we analyzed, by using Taguchi analysis, we analyzed at what percentage or at what level we are getting the better values. Maybe here you can conduct more number of tests and you can generate more data, and maybe you can use machine learning techniques, etc. so that we can find out the exact values also, because here we are taking whatever the levels we selected, among that we are taking. It is 1:2% or 2:1%. It may not be exactly 1:2. It may be fraction also, right? So that if you conduct more number of experiments, maybe you can get the more data, so that we can optimize with any of the optimized algorithms or machine learning techniques, etc. So then we took the S-band ratios, etc. And finally we got this is the optimum, that is the base oil is sesame oil, and the particle percentage is 1:2, that is CNT and MOS2, and then the surfactant is SDS, and the surfactant percentage is 15% of the nanoparticle weight. So like this, then the same thing for confirmation, the same thing again we prepared with same composition, and we tested for sedimentation as well as zeta potential value, so that once we are confirming that, then we are going for machining. So in the actual machining environment, then we are going to use this cutting fluid, hybrid cutting fluid. So then we took a normal lathe machine and we are going for turning operation. So these are the conditions all, what is the cutting speed, feed rate, depth of cut, etc. And we are taking MQL at a flow rate of 10 ml per minute, etc. So then we took the ratio of CNT to MOS2 is 1:2. That means if we take 1 gram of CNT, 2 grams of MOS2 is taken, 1:2 ratio. And then the total this weight percentage in the base oil, that is also optimized, okay, in the later stage. Then results we got in the cutting force, that is meters compared to dry machining and compared to conventional machining, we got better performance. And here actually the thing is, more than this performance, the main motto of this one is biodegradability, right? So we have to avoid that pollution or environmental damage to the one, but at the same time we have to check the performance also. That is why these are the performance tests. So these are the cutting conditions we used, and then we got this improvement. Then again here we took some percentage of hybrid nano cutting fluid. But what percentage? If you vary that percentage, then again performance may be varied, right? So then what is happening? First of all, why improvement we got? We need to understand. That is what actually important thing. So this is the workpiece material. This is the cutting tool material. So the workpiece is like this and cutting tool is cutting, right? So whatever I have shown the primary deformation zone and secondary deformation zone. So in the secondary deformation zone, the chip is moving on the tool. So between these two, we want to reduce the coefficient of friction. So how it will be reduced? So like this. So between the workpiece and the cutting tool, actually the nanofluid or hybrid nanofluid, whatever we are sending in the MQL, using MQL, that means using the compressed air mixing with this cutting fluid and sending to the machining zone like a spray. Okay. So now that is what we are sending here. Then this is the bond, this is the actually MOS2, and we have MOS2 molecules are there, and here we have the CNT molecules are there, because these two are not reacting. These are like a suspensions in the oil. So once we are sending between these two surfaces, these are acting like that, and because of this bonding of vegetable oil, bonding of MOS2 and the structure of CNT, etc., these are all formed as a film or a layer, thin layer between the surfaces, and the coefficient of friction is reducing. So because the coefficient of friction is reducing, then the heat generation may be slightly less in the secondary deformation zone, and also because of the high thermal conductivity of CNT mixing with oil, then the heat will be absorbed by this one, right? Of course some amount may be evaporated because of these high temperatures, but we observe the heat, so that the heat is absorbed by this hybrid nano cutting fluid, as well as the lubrication is also created between the surfaces. So this is the CNT. So this is actually, if MOS2 molecule is there between the tool and workpiece, and if CNT is there, and the CNT and MOS2 alternatively are there like this. So CNT is like this and MOS2 is like this. So then because of these alternative layers and etc., then what will happen is the MOS2 particles are like this and CNT is like this. So it's become a sliding action, and then these particles or these layers are going here and here. I think this diagram, do you remember? In the first slide I have shown primary deformation zone, secondary and tertiary. So here we are supplying this cutting fluid. So like this, these nanoparticles are going into secondary and tertiary deformation zone like this, and then the sliding action is creating. Okay, and also here we are supplying this one, here between the chip and the tool, between the tool and the workpiece, etc., we are able to satisfactorily send this hybrid nano cutting fluid with the help of this MQL equipment, so that we can able to reduce the coefficient of friction, and also we can able to improve the heat absorption, that is extracting the heat from the machining zone. So then this combination, that is sesame oil based, the combination of CNT and MOS2 hybrid nano cutting fluid are proved to be stable based on the sedimentation test and zeta potential test. And then the same thing we used in the machining, that is the 1:2 ratio of hybrid ratio, as well as the SDS surfactant. What is SDS? Huh? Sodium? So what is sodium? D means? This is sodium disulfide. Okay, so that one is better. So then we improved the machining performance. So then this is the actually we are using, that is again the concentration of hybrid nanoparticles we can calculate like this, and again this concentration we can vary. Previously we used only one weight percentage, right, and now within weight percentage we can change, but within this the ratio is 1:2. Within this the ratio is 1:2. So we can change the concentration of nanoparticles in the base fluid so that we prepare the different this one, and then we check the basic properties. Like actually the previous one is just a confirmation test whether this hybrid nanofluid performing better or not. So then after going for different concentration, then we can check what about the viscosity, what about the thermal conductivity, and what about the coefficient of friction, right, and etc. We can check the basic properties because we want these three, right. We want better lubrication, we want better cooling action, and we have to reduce the coefficient of friction. So like that we check. So we use a rheometer for testing the viscosity, right, and then with the different percentages. Normally it is common, if you are increasing the weight percentage, the viscosity is going to increase. But at the same time here we need to understand one thing, if it is more viscous also, the flowability is decreases. So which is not required for us, but at the same time we want a viscosity. That's why some arbitrary value or wherever we are getting the saturated value, that we have to verify. So this is actually the viscosity, and then we use thermal conductivity, hard disk thermal conductivity analyzer, so that we check the thermal conductivity. So if you are increasing the weight percentage, then thermal conductivity also increases, viscosity also increases, and then this is at a different percentages, the thermal conductivity values, and then this is the coefficient of friction. So we apply the same thing and we can find out what is the coefficient of friction between the surfaces. That is we use the tribometer or pin on disc operators, etc. Then we can find it. So between the two surfaces, actually the hybrid nanofluid will be like this, right. So maybe carbon nanotube, maybe MOS2 particles. We don't know exactly how these will be, but this is our assumption. If you are mixing properly and you are using the same hybrid nanofluid, we are assuming that these are equally distributed, and so that we get the better this one. That is why we are checking the ratio 1:2 or 1:1 or 2:1, etc. Then here we are getting a low coefficient of friction for this one, for this combination. What is this 3 and 4? That is at 1.5% and 2%. After that again coefficient of friction is increasing. That is what I told you. The viscosity becoming more and it becomes obstruction for the flowing action. Then again coefficient of friction increases. That is why we got better value at a percentage of 1.5 and 2 weight percentage. Then we have to check this one, which is better in the machining operation, right. So based on this one we selected the 1.2 and 2 weight percentage. Of course the lowest coefficient of friction 2 weight percentage. Based on the thermal conductivity and viscosity and this one, we selected finally 2 weight percentage, and then we used again in the machining operation, because previously we tested only at a particular speed, feed, depth of cut. Okay, then if you are changing the speed, then what will happen? Because if the speed is high, then the heat generation is more. If the heat generation is more, then we require more cooling and more lubrication. So at high speeds, whether it is useful or not, at lower speeds maybe it will be useful, right. So at higher speeds may not be useful. Like that we have to test at different speeds or different feeds, etc. And these different percentages also we verified. So these are the conditions where the nanofluids are performed. So this is the cutting force, right, different cutting forces, and this is cutting temperatures, right. So this one is having high thermal conductivity, that's why temperature may be less, okay. And here again the cutting force is less for this one because the coefficient of friction is less. That's why one property may be useful to reduce the cutting force and other property may be useful to reduce the coefficient of friction, or that is to reduce the temperature. And then if you check the surface roughness, that is surface finish or surface quality, then again 2% may be better. Again slowly it is increasing because the coefficient of friction is more, and the flank wear is also like this. Of course flank wear may be less because if it is temperature is less, then the flank wear is also better. So like this we are getting the machining performance of different nanofluids, different percentage, etc. Then we can able to finalize what is the best composition and what is the best base fluid. Like that we can try different combinations. Whatever the possible is there, you can try any one, but this is what within what we are taken, this is the better combination, right? So if you are changing the combination, maybe the performance maybe changes. If you change base oil, or if you change nanoparticle, or if you change the percentage, then the performance may be different. Okay. So like that in this case we studied at different machining conditions, different percentage, etc. And finally we come to some conclusion, that is the CNT and MOS2 nanoparticles as 1:2% in sesame oil with the SDS surfactant, and surfactant weight percentage is 15% of the nanoparticle weight percentage, and also 2 weight percentage is the nanoparticle weight percentage in the base fluid. So this combination is given better performance at all the conditions. Okay, right? So this maybe you can try any machining operations or any other applications or any other things. Okay. So this is what one application of this nano fluids, that is hybrid nano fluids as coolant and lubricants, right? So do you have any doubts? Please ask me. Yeah, that's what I told you. See, suppose you want only reduction of heat or only absorbing the heat. So we select nanoparticles which are having high thermal conductivity. So maybe CNT is having high thermal conductivity. So then you can go for only single nanoparticle. But here application is we want thermal conductivity as well as lubrication. That's why we go for the hybrid. But some other applications, maybe in the heat exchangers, or maybe in the some radiators cooling, or maybe in the some micro channels used in the electronic components, etc. Like your laptops, if you want to cool, right? There are micro channels where the liquid will be there. Okay, high-end computers, etc. There we want only the cooling action. Lubrication is not required. Then we select the nanoparticles which are having high thermal conductivity. Like that, depends on your application, you have to take. And also there I don't want base oils. Maybe we can use water. Because I don't want any viscosity, I don't want any reducing the coefficient of friction. This is the machining application where I want lubrication also. That's why the base fluid is a oil. That is also especially vegetable oils to go for the biodegradability or eco-friendly cutting fluids. Okay, that is what you have a lot of literature. You can try anything. This is the procedure or whatever, just this one. Okay, so if you have any doubt, please ask me. Otherwise, we can close this session. Okay, right. So if you have any doubts, maybe you can mail me also later.